मेरे मेल पर भेजिए ना, पुराने वाले पर, क्योंकि मैंने यहाँ दूसरा मेल खोला ना। हाँ बस बस बस
मेरे पास एक ही है आपकी।
एक मिनट एक मिनट
राकेश जी आ गए आप ऑलरेडी? आ जाइए आप। आपकी तो आपने वो सेट करने ट्राई किया आपका? और
एक मिनट ले हो लिया। मैं इसको रखता हूँ ना डाल के।
इसको मेल नाम हटा के शिखा करते हैं।
हाँ बस मैं इसको डाउनलोड करता हूँ एक मिनट।
मॉर्निंग का सेट हो गया आपका?
इससे अभी तो कर दिया सर।
अभी फर्स्ट कौन है?
सुरेश सर है
सुरेश सर ना?
सर। आगे ऑनलाइन आ गया सर।
मैं आपने इसमें कर दूँ?
फ़ोन से कर लो सर आपको।
Good morning, Dr. Suresh. Good morning, Dr. Suresh.
Good morning.
Sir, you can share your screen. You can share your screen now.
You have what, 2 minutes? You have what, 2 minutes to begin.
Thank you. Thank you.
स्टार्ट।
I think Suram sir is not coming out. Join.
नो सर। जी
Sir, you want more time? You can take more time.
You want
You can take more time. Studying. So much. Thanks a lot.
गणेशाय नमः, सरस्वत्यै नमः, श्रीगुरुभ्यो नमः, हरि ओम जातवेदसे सुनवमसो ममराति यतो निदहति वेदम् स नः पर्षदति दुर्गानि विश्वानावेव सिन्धुं दुरितात्यग्निः तामग्निवर्णां तपसा ज्वलन्तीं वैरोचनीं कर्मफलेषु जुष्टाम् दुर्गां देवीं शरणमहं प्रपद्ये सुतरसि तरसे नमः अग्ने त्वं पारयानव्यो अस्मान् स्वस्तिभिरति दुर्गानि विश्वा ओश्च पृथ्वी बहुलान उर्वी भवातोकायतनयाय शय्योः विश्वानि नो दुर्गः जातवेदः सिन्धुं ननावाधुरितादिपर्षि अग्ने अत्रिवन्मनसा गृह्णानास्माकं बोध्यविदातनूनाम् पृतनाजितरुं सहमानमुग्रमग्निगुं हुवेम परमासदस्तात् स नः पर्षदति दुर्गानि विश्वाक्षावद्देवो अतिदुरितात्यग्निः प्रज्ञोषिकमेभ्यो अध्वरेषु सनार्चवो दानव्यश्च सत्से स्वाञ्चाग्ने तनुवं पिप्रयस्वास्मभ्यं च सौभगमायजस्व गोभिर्जुष्टमयुजो निषिक्तं तवेन्द्र विष्णोरनुसञ्चरेम नागस्य पृष्ठमभिसंवसानो वैष्णवीं लोकैहमादयन्तम् कात्यायनाय विद्महे कन्याकुमारी धीमहि तन्नो दुर्गिः प्रचोदयात् ॐ शान्ति शान्ति शान्तिः।
With the blessings of the Divine Mother, we are into the second day of our third international conference on recent trends in nuclear physics, which we are holding it this time in hybrid mode. We are extremely happy to have Dr. Suresh Kumar, Professor of Physics in Delhi University, who is with us to share this work this morning. Dr. Suresh is very well known in nuclear physics in the nuclear physics community. He has worked with IUSC in experimental as well as, of course, now he does his own theoretical work and has many publications. In fact, we are just having him here. He had come to us at the entry of Professor for Central University and been a regular support to our international conference from the inception. Thank you, Dr. Suresh, for your precious time and constant support. Please take over to present your work today.
Very good morning. I'm audible.
You have to
Am I audible?
I'll
Yes, sir. Okay. So first of all, I thanks and give me opportunity, but I also regret because I want to be attended in the personally at the and I also feel that this conference has created a very different environment, particularly in North Indian context, or particularly for nuclear physics to have in North India domains, and which is a very high, very good point, because when we talk about nuclear physics, we most of the time we stick with the Kolkata area or in south or in. So that's why I want to thank that this type of series, which is started organizing by Dharamsala University, Central University of Dharamsala, is very good point. And being a local, I would like to say that तुम्हारा बड़ा बड़ा धन्यवाद मुझे तुम्हें मौका दिया. So I want to say that I praise you and I thanks that you have given me opportunities. Today what I want to talk is a very preliminary work which I have done with my particularly with MSc students. Okay, so what is the title? I want to systematic study of single particle or whole state of or a nuclei with where proton number is taken for 41 to the nucleus and with the even n and the neutron. So I have planned, I will introduce and then I will talk about data on single particle, holes and how organized how this data is done. And then I will put some results on odd n nuclei and then result on odd n. When we are talking about odd a nuclei, we have to consider odd z separately with even number of neutron and odd neutron with even number of proton. And then summary and future scopes. So low-lying excited state of a odd a nuclei are important to study the single particle configuration because these are where the single particle states are mostly populated. Also, because of different dynamics we have different dynamics where we couple the intrinsic states with the what we call that coupling of a particle and whole with forcing. So it's also these are single particle state not only giving us the validity of the single particle model, basically the cell model or the Nielsen model, but it also gives us the validity how with Bohr when Bohr is changing this shape, axial and non-axial shapes. So, if you find in the literature, there are a lot of studies done, and I am blessed with that because the work is done by Professor P.C. Sood and Professor A.K. Jain. They are my mentor and great mentor, you can say that. And that has mostly focused on rare earth and actinic series. And also systematic beyond rare earth nuclei and actinide is possible. And further now, because the last 10 to 15 years we have now also available data for the neutron-rich nuclei. So the idea of choosing this, and also we want to see that the magic number which we have, conventional magic number, how we are behaving when we are going to the spherical. So what we have done that, we have taken the data from National Nuclear Data Center NNDC site and focus on the nuclei which are falling between A is equal to 91 and 149. And then data is organized in two sets. The first set is where atomic number is 41 to 59, but neutron is taken in the range of n is equal to 50 to 80. In the second data set, what we have done that we have considered the neutron number from 49 to 81, but we have taken the z is equal to 32, 64 or 68. And then we look on the ground state and the particle excited state are identified. And we just done the systematics of these as a function of the neutron number and d. So if I see that how we evaluating the number of particles or cell model. So when I am filling the proton and starting from atomic number z is equal to 41, I am filling the 1d9.5 and then I am going 1d7.5 and 2d5.2 and then 1h11.5, 2d3/2 and 3s1.5. Similarly, when I am going for the neutron numbers from beyond this n is equal to 50, I am filling the 2d5.5, 1d7.5 and 1d3.5 and 2s.5 and 1h11.5. So particularly when we are looking the ground state property, excited state property, so in case of the neutron, we must see that these are the single particle orbits which have been responsible for these ground state and excited state. And for the proton case, we are filling from this and to this, so it means that I will get most of the states. So now these are the data set which have taken, and here we have whatever this data set where we have the proton number we have taken the odd and neutron number taken for and we try to be here in this color. These are showing the proton rich nuclei, the neutron rich nuclei and stable nuclei. So we try to analyze this most of the data. Now these are the example how we produce the data set. So we have tried to fill, as we are filling the vacancies of the particle, we are same way we are trying to do this. And then we are putting that, here 0 in this data mean that is the ground state, and when dash is written that data is not available at particular data set. So this is the organization of the data set, and it is organized on the base of your proton number and proton number increasing, and then atomic number. So this is the outcome when we put the ground state and start filling from the 41s to 43, 45. So we found that when we have the neutron very close to the magicity, the ground state spin of these most of the nuclei in the roadside for when Z is equal to 41 is given by 1 G9. But as we cross the neutron number beyond 58, so the higher cell come down and they try to fill. So this is also because the deformation is coming, so that is also coming. So if you see that most of the nuclei when we go above, and then if you see the more spherical nuclei, you find that for indium case, we feel that all the ground state spin is given by the 1G9.5, whereas for Z is equal to 51, we have a change in the configuration beyond 70. And that GB half and this, so it means that there is a change in this single particle structure as the neutron is increasing, that is the neutron asymmetry increasing and by that risk. And so this is there, and also we found that the occupancy. So you can see that how the occupancies for this ground state is filled when we consider the most of the cases. So as we found that for this case 1/2 negative spin which is coming from P half is mostly about 10 nucleon, and G9.5 is about 30 nucleons, and then S half, G7 half is filled by 42 nucleons, and then F5. And surprisingly I saw that because H11.5 is filling much more orbits. So ground state spin, I did not find that the nucleus, but it may be possible that because we have not covered beyond Z is equal to 60, so that can be said, but I only see only few nucleons which are giving the H11 orbits, the ground state. And now if we see the behavior of how is this single particle state, and I want to say that when we are trying to figure out this single particle state, it is very important to study their excitation as a function of neutron number of proton, because that tells that trend of these energies will tell you that you are picking the right identifications. So if you see that for Z is equal to 41, Z is equal to 43, and Z is equal to 43, and remarkably in Z is equal to 41 you don't have only the 50 is magicity, but the 56 is also appearing as a magicity number. And as you go higher, this 56 can diminish, but you find that the Z is equal to 64 is appearing the minima in most of the cases. Simply that is the one of the deformed case which is well known to us also. And then for so that's how we can keep on the identification of this, because the trend of your excited state has to be preserved when we are going to understand the excitation function. And particularly here in this example, I have presenting the whole state are presented by the unfilled boxes, and the particle state are there. It reflects that the occupancies as we go genome, and it will be also say that excited state which we have. In case of Newton, the Newton case, and we have started from Z is equal to 32 and go on beyond go to 66, because I want to be distinguished. I want not to do the same work which is already done in the actinide or rare region. So that's why the region of fusion is also here. And so again the data table is organized in the very same way. This is one of the examples how we analyze it. And then if you see the again for the when we are filling the neutrons and going from 49 to 81. So we are filling now again G9 half and then D half and 7 half. But we have not seen any changes which are feeling order changes which are given for 2D half and low. But most of the cases they are preserving. But in case of a neutron case, proton case, we see that as we increasing the proton number, in the neutron number, this state get flipped, which we not seen in this case. And then also we see that the highest occupied state is not H11 it is coming in spin and that is also this case, and that is what we understand. And when we plot it as a function of number of nuclei which are seen in the ground state, so we see that the occupancies of D5 is more because D9 is 1. Because we have only considered few nuclei beyond Z is equal to N is equal to 1. So that's why the occupancy, but that is the considered case. So this is the example showing that for N is equal to 50, how the magicity of N is equal to 40 conserved. And similarly for N is equal to 51, the 40 city magicity is preserved. But as you go higher in the region, so the 40 city magicity that is equal to 40 or magicity is not very strong, it goes faster. However, for N is equal to Z is equal to 50, the magicity is reserved most of the cases. And if you see the further example of citation energy, you see that till N is equal to 71, because the data is not available, because those cannot be registered. But if you see still N is equal to 71, clearly the magicity of Z is equal to 50 is reserved. And then you see that the further occupancy is shown. So the conclusion is that what I want to summarize that the LoRa inside the state of God nuclei are compiled to understand the single particle or whole configuration. And this systematic experiment of single particle energies were discussed on for odd A with proton number ranging from 41 to 10 is equal to 51 and the 49 to n is equal to 81. The evolution of the ground state spin are tabulated and occupancy of single particle were discussed, and we found that in case of proton, when we are feeling, as the neutron, more and more neutron coming, there is swiping between G7 half and D half for the ground state spin. And also when we, for the example, it appears that for case of proton, Z is equal to 40, 50 and 82 are reserved the magicity. However, as the neutrons increases, the 40 Z is equal to 40 is not remain the magicity. In case of a neutron, there is strong magicity shown by most of the case when we have n is equal to 50. So this is what. But in some magic, n is equal to 56 appear very close to the near n is equal to near z is equal to 40, and we also seen that the maximal deformation occur near n is equal to 64 because all these single particles state which are plotted as a function of neutron number. We found that the minimum energies of these states are of the at n is equal to 64. So in the future what we want to, because as we going the evaluation, we are going from the spherical nuclei to strong nuclei, so we want to study the band properties so that we can see that identification of these cytosis is very high. So we want to study the band property like band moment of inertia, parameters, etc. And the configuration from the Wilson diagram, and then future we want to examine for the order of nuclei, because that will give us understanding of neutron and proton interaction, how they are taking place in this nuclei. So that's all from my side, and thank you for giving me
Any questions, please? यहाँ से बंद कर, वो लैपटॉप ऑन है। Thank you, Dr. Suresh. We have next speaker, Dr. Poonam Jain. She is from the currently an assistant professor of Department of Physics, the Aurobindo College, University of Delhi. Dr. Poonam Jain has completed her PhD from Indian University. Did her entire in computer science from Delhi, and of course her BS in MSc also from University of Delhi. She has many papers to her credit, both in international journals and she also regularly participating in DA symposiums. And so this time, first time she is participating in our international conference. We welcome you and thank you for taking the initiative to connect with us and trying to be a part of our conference. We're extremely happy to listen to your work. It is very similar to the kind of work that we do. She is also in nuclear structure. Everything means from Professor A.K. Professor A.K. is favorite subject of physics. So we are the grad students, are great grad students. So you also will be support on our lines. Maybe great friends. So the idea of this conference, as Professor Suresh was telling, actually somehow it has become popular in North India. And the idea is to give opportunity to all nuclear physicists because we are a declining tribe, which I want to revive and ensure that we are on par with material science guys. Okay. So extremely happy each and every one of us comes, and we hope that we can make again nuclear physics very vibrant in this country. So thank you, Dr. Poonam Jain, for connecting and offering to share your work with us. Over to you. Please share your screen and start.
Thank you, sir. Thank you so much for the kind introduction. And thank you to the organizer for providing me this opportunity on the last minute. And I'm really very happy because very few conferences focused on the nuclear structure. I hope I'm audible.
Yes.
Thank you. So I'm very happy to connect with this conference because hardcore this is from the nuclear structure physics. So let me share my screen so that I can present my work. Yeah, is the screen visible? I hope the screen is visible. So the topic of my talk is the level scheme studies in actinide reason. I'm thankful to the organizer of online international conference on theoretical aspects of nuclear physics, and I am looking for more opportunity to collaborate with Suresh sir from the university and of course Shastri sir and all the eminent professors present over there to extend my work. So the plan of my talk comprises of the introduction on the reformed nuclei, then the motivation behind the work, the model is the two causal particle Baker model, which I will explain in brief, and then the result of discussion, and finally I summarize my work. In the introduction, initially I just wanted to tell the stability and the decay modes. We all know whenever we have the lighter element and the NY-Z ratio is 1, we have the stable nuclei which is depicted by the pink line in the diagram. And these are the value of the stability, like the beta emitters is shown by the blue color, the peach color is showing the beta plus emitter, the yellow is showing the alpha emitters, and the green one is the spontaneous fission. So in the serial chart we can see the heavier element when the ratio of NY-Z is more than 1, and there are certain regions which are near the neutron rim line and the proton rim line, and of course the nuclei which are more than mass 209 undergo alpha decay, and above 240 will go for the spontaneous fission. Now what is the reformed nuclei? I mean the nucleus which is away from the spherical shape is said to be a reformed nuclei. It can be ovate or prolate. So So oblate, of course, having the quadrupole moment less than 0 and the prodate is having the quadrupole moment greater than 0. And the collective model was first time given by Bober and Robinson for actually symmetric potential. Then the anisotropic harmonic oscillator, we all know, is having the potential like half n omega perpendicular square, where omega x is same as omega y and omega z is the third axis. And these represents the frequencies of the simple harmonic motion in the perpendicular and parallel to the nuclear symmetry axis. And we write in the form of the nuclear deformation like omega naught times 1 minus 2 by 3 delta and omega naught times 1 plus 1 upon 3 times delta. So the omega naught cube gives us the volume conservation. And similarly, we know how to find out values for the anisotropic harmonic oscillator potential. So this is the formula which describes the eigenvalues for the anisotropic harmonic oscillator. Finally, we reach to the energies of the spherical harmonic oscillator minus the correction term, and which is proportional to the deformation. Here I will use the Wilson model as Sir and Suresh sir has already discussed. We have the possibilities to go further with the help of Wilson model. So we have added the term proportional to H square and the spin-orbit coupling term L dot S. So finally, the modified harmonic oscillator or the Wilson potential which we are using over here is having the potential initially which we have given along with the spin-orbit coupling term and the H square term. And carbon and mu are some adjustable parameters which we use to adjust during our calculations. H square term always depends on the effective potential of particle near the nucleus. These are the diagrams which which I have shown for Z or N less than equal to 0, which is question numbers at 8, 20, 28 and 50. So for the particle reflective excitation state, we know due to the time reversal invariant, the single particle state are always doubly reflective. In case of forward linear, the projection of angular momentum for proton and neutron configuration coupled together in two bands, K plus and K minus. And the relative energy ordering of the K plus band is determined by the GM theory. So GM theory plays an important role here, and the important outcome of the residual interaction is shifting in odd and even rotational level is known as the Liouville shift, which I am going to focus in my work. And these are the diagrams which are showing us the K plus and K minus, the parallel coupling. This diagram is basically the parallel coupling of odd proton and odd neutron angular momentum leads to the formation of band with quantum number, and this is K minus band in W odd nuclei. One is depicting the K plus configuration, another one is depicting the K minus configuration. There are certain properties of two quasi-particle rotational band which we usually focus in our work: is signature splitting, ordinal staggering, and signature inversion and signature reversal. I hope everybody knows about it because all our nuclear theorists and experimentalists over there. So these properties are very useful in the study of the deformed doubly pure and doubly even nuclei in the actinide and rare. Now I want to tell what is the motivation behind this work, because most of the work, as Sastry sir has said, are done by Professor A.K. Jain and his group. I am also a part of this group. So most of the work for the Liouville shift and the MP residual interaction using TQ-PRM model has been done for odd as well as for even nuclei in rare earths in great detail. But very few calculations have been done for the actinide region. The reason again the insufficiency in the data available by the experiments. So that is the principal motivation behind this work. Since we have not available with much data from the experiment, so let's have some theoretical calculation and let's achieve something new, which is surprising for all. So one step which we have taken here, we have revisited the role of MP-residual interaction and how Liouville shift act in the actinide region. And second, we are able to deal with the theoretical explanations of K0 bands in order of actinide region using the TQ-PRM model. And we have reached to some of the challenging problems, and some problems are still there to address. So this is the theoretical model to quasi-particle plus rotor model. So I don't want to go into the details. I just give you a glimpse of it. The total Hamiltonian for ordered system is composed of two parts. One is the intrinsic part and the other one is the rotational. Further, this intrinsic part consists of the average potential, the pairing term, the vibrational potential, and the residual interaction. And the rotational part is composed of the rotational part plus Coriolis term, particle, and irrotational, which are defined as this. These expressions, and J is our moment of inertia with respect to the rotational axis, and this is the pure rotation part. X rotational 0 is the pure rotational part, and rest of the terms are having the same meaning just like we have in the literature. The contribution because of the rotor particle. Suresh sir is saying something.
No, continue करो.
Okay, so which can couple two-state satisfying condition delta K is equal to 1, and particle is the contribution corresponding to particle coupling, which will contribute to the delta K is equal to 0. Irrotational is the contribution because of the equality. Here we have used the Nielsen model wave function for the neutron and proton. So we have reached to the intrinsic state, and K is the good quantum number, and set of the basis for the unperturbed Hamiltonian can be given for K is not equal to 0 like this expression, and for K is equal to 0 we have taken into the calculation. Then we have applied the Petit procedure and selection of the parameters. So this is the empirical formula for the UV shift, which we can compute using the energies of two adjacent levels in K0 mass, and the least square fitting method is used to provide the value for the variable parameter. And here we have used in the Nielsen parameter the kappa for the proton as 0.05 level 7, mu1 for 0.650, kappa for the neutron is 0.0635, and mu for neutron is 0.325. So A is given initially the value which is 5.5 to 5.5 keV, which is adjusted later. Now the overview of my work. In this work we have focused on the specific problem of UV shift in the actinide region, because already the error region has been explored in great detail. We have carried out the analysis of all the K is equal to 0 bands available in the ordered actinide region using the DRM model. The analysis is carried out in the hope so that we can have a clue for the origin of UV shift. And UV shift values were determined for all the cases which are free from the Coriolis effect, both the diagonal and the non-marginal, which I have listed in the part. Also, we have tested the applicability of the empirical rule which is proposed by the Fritz in 1980 in the actinides. And now, the banded energies for certain bands which are not available, we are able to predict those in 238 Neptunian or 240 Ambitious. And the banded energy for K0 band is 238 Neptunian, that is another band, is also predicted. And the amazing feature which finally conclude the work is we are able to propose the level structure of K0 and K5 GM partner bands in 240 Ambitious, which is given in the experimental data. So I am coming to the result part. In total we have approached 11 cases which are available in K0 bands in deformed order actinide region, which I have listed here. The experimental data where we have given the configuration for the respective band 5/523 and 5/622 for the neutron. This is the configuration, and the nucleus are Neptunian and Ambitious. And the parent orbit we have listed in the second column. The nature of the K0 band, triplet or singlet, is also mentioned. Here, as we can see in the experimental data, we do not have the band height energies available for 238 Neptunian and 140 Ambitious for this particular configuration, which we have calculated using our model by adjusting the initial parameters, and we have also calculated the UV shift. This is the calculated UV shift, and this is the experimental UV shift, which we have having the same nature. And in all the cases, as we see, these 11 cases, out of these 11, 8 cases are having the same nature. Similarly, in the second configuration of 238 Neptunian, 5/642 and 5/622. Again, the experimental banded energy is not known, which we are successfully able to predict using our calculation. So another table is showing those cases in which we are not having the compatibility of the expected favor spin and observed favor spin, which was given by the Fritz. So, and one more case is there, 1/400 and 1/631 to 38 Neptunian, in which the experimental banded energy is not known and we are able to calculate it. These are the diagrams which are the PQTRM plots for the energy versus the strain. Again, for all the cases which I have shown above, but here I want to focus on the all-level stacking, which is one of the most important property of the bands. And here we have represented the experimental data, which is marked by the star, the theoretical data with the condition, and the data shows the theoretical data without condition. In these all cases, all 8 cases, what we can see, whenever there is no role of leadership, we have a straight line, as we can see. So this data is free from the numission for K0 bands. Right? And these are the another cases in which we are not getting the straight line when the leadership is not playing any important role. This is the most important part of the study is the level scheme of the K0 band and K5 band into 40 evolution. As we can see in the experimental data, on the left side we have the experimental data. From this it is very clear that in experimental data the spins are having the same nature. These are the spins which are having the same energy. 3 and 5 are having the same energy, similarly 6 and 8 are having the same energy, and 4 and 5 are having the same energy. So this mystery is resolved by our calculation, and we reach that 4 and 5 are having a slightly different value, but they are different from each other. Similarly, 3 and 5 are also having a slight difference in the value, and similarly we are able to resolve 6 and 8. So we can say these are degenerate states somehow, 4 and 5, but not all. And same the problem with the K5 band is also resolved. We are able to predict the resolved level scheme for K0 and K5 band for 240 dimension. Finally, the conclusion, we have carried out the analysis for K0 band. In total, we are able to list 11 cases which are available in the odd-odd actinide region. The banded energy for certain band for this particular configuration in 38 natrium and 240 magnesium are predicted. The banded energies for this particular band and this particular band in 38 natrium are also predicted. The Lubitsch values are determined, and we are able to see that these are free from the coverage where both dimer and non-dimer. Also, we have tested the applicability of the empirical rule which was proposed by this in 1980, and this is still applicable in the actinide. And in 8 cases, the rules work very well, and in 3 cases, the rule does not work, which needs more analysis. And we have also plotted the staggering plot, which shows the observed staggering in leadership, and En is equal to 0, the staggering is means whenever there is no role of the leadership, the staggering pattern is flat. So, another important thing, the spin parity assignment of several bands of configuration into 40 ratio is resolved, and we are able to predict the magnetic level scheme for K0 and K5 band into 40 ratio for a particular configuration, 5 half, 523 and 5 half, 622. So this level scheme is unique, and obviously it is helpful for the experimenters and theorists. So one of the long-standing puzzle in nuclear structure physics has been correct prediction and explanation of Lubitsch shift in uniform order nuclei is realistic. So this is all from my side. Thank you for your kind attention.
Any questions, please? No?
Can you hear me now?
Yes.
Excellent results, but what is your future plan?
Yes. The future plan is basically right now I have not shown all the other properties like signature partner pair, signature inversion, signature reversal. So with the help of this tentative level scheme, we are able to go for the other properties of the particular band for the actinide region. I have initially told the problem with this reason is basically the unavailability of experimental data. We have very few bands with the level schemes which is having the spins and the energy. So only we have focus on K0 band, but in future we can go for K not equal to 0 bands as well, and we can find the properties like signature, inversion and all.
Thank you, sir.
Thank you, sir. I would love to answer any other question if participants have.
Thank you, madam.
So you are on mute.
I'm on mute. Thank you. Can you hear me? Yeah, you are to switch off.
Yes, sir. Yes, sir.
Thanks a lot for your, and as you said, we will interact further over the internet and then try to take your work forward. Certainly, it's an interesting talk. Now we have Dr. Rakesh. Dr. Rakesh Kumar is a very senior scientist at Inter University Accelerator Center in New Delhi. He has joined the center in 1998 after obtaining his master's from Pune University. And then he did his PhD in collaboration with GSI Germany and obtained the PhD from Maharaja Sayaji Rao University of Baroda, Vadodara. He is currently a core member of the Gamma Spectroscopy group. All of you have heard about it yesterday also. And his primary research interest is in the experimental study of nuclear structure physics using Coulomb excitation technique. And also the study of nuclear reaction dynamics in light and heavy ion interactions by complete and incomplete fusion reactions. And especially is very well versed in the field of instrumentation. He had been a visiting scientist at GSI and also at Warsaw in heavy ion laboratory in Warsaw. There's more than 200 publications, and he not only works in nuclear structure, now currently also is extended his applications to material science and atomic physics. Most importantly, he is from Banike, हमारा हिमाचल से बात करते हैं. So we should be very proud that he has traveled all across the country and the world. And that is what is the inspiration we want for our students. Right? See, that's what we always believe in our department. If X can do something, I can do better. Right? So, already he has shown you the path. He has been to Pune, he has been to Vadodara, then he has been to Delhi, and then Germany, and Warsaw. 40 countries. 40 countries he has visited. So it's a very huge target he has kept for you. So you have overtraveled man. So he is a very, very versatile personality, as you can see. I really look forward. Sir, now it's up to you to inspire the young generation and ensure that all of us follow your footsteps.
Nico is there.
Okay. Thank you, man. Thank you, man, for the dance.
Sir, so
ताकि हाँ वैसे सब कुछ सेट कर लीजिए जो भी लेक्चर इससे पहले एक आके डिस्कनेक्ट
ये सारा प्लेग्राउंड जो है ये आपके डिस्पोजल पे आप कहीं से भी करें।
इनका नहीं हमारा ये दूसरे को दे देना कहीं भी करो
समझदार आदमी है।
दोनों मनोज कुमार शर्मा आपको जानते हैं श्रीवास्तव जी का ग्रैंड स्टूडेंट एक्चुअली अपने लैपटॉप से कनेक्ट करना चाहते हैं जो हमने गैस एनिमेशन की शो वांट्स टू शो फ्रॉम आवर लैपटॉप देन ऑफ दिस मॉर्निंग तो कनेक्ट हो गई हमारे शिवम सर है ना यूनिवर्सिटी जम्मू से आ जाना था पठानकोट तो पहुँच गए राकेश मनोज सर 4 लोग ऑफलाइन
You're audible.
Okay. Good morning, everyone. Dr. Rakesh Kumar. तो मैंने ये टॉक किया आपको and plans to compare. It was great. It was presenting my topic when John and I was long back. आज की टॉक मैं आप लोगों को बहुत एक्साइटेशन के बारे में बताऊं. So it's not only that I go and speak in English and some high-five things. You say sir, what is that? No. You need to know what we are doing. So what you see in this picture is your university on my collaborative account. The word that you can see Warsaw, University of Warsaw, GSI Germany, from Japan, University, Singapore University, DSU people, Punjab University, and many others. Okay. How much is the delay?
हाँ क्या हो रहा है राकेश जी नहीं पता
देखना पड़ेगा। चलिए एक से दे देते हैं, प्रॉब्लम नहीं है।
यहाँ से एनिमेशन आ जाएगा।
आ जाएगा ना, इसी में लगा रहता है क्योंकि कंप्यूटर भी रहेगा। Because on Wi-Fi now, but we don't put it.
I know. Okay, you know, whole night you worked on it actually. You wanted to bring it down to the level of students. और कहीं से कुछ ट्राई करें तो होता है।
Actually, wanted close to that screen so that he can
भी करें।
I can still give it to you. Okay. I'm audible now still? हाँ, सुनाई दे रहा है तुमको? हाँ, change करना बहुत मैं बोलूँगा आपको। Okay, next slide please. So, let's see that where we are and where this place is at. So when the invitation came, I thought how to go. Then I take a flight. Let us explore the whole stage. So we car निकालेंगे हम right here also. Next please. So IUC is here and your Shahpur Central Union is there. Then we started driving. Next please. धीरे-धीरे सफर चलता रहा, काफी नीचे हम पहुंच गए आपके शहर. It took us only 10 hours to drive at a distance next please of 562 kilometers. So then there was somebody to say welcome to Shahpur. Next. So let us now get serious to the work. What we have in India are three accelerators. First of that is our place, Inter University of Bangalore, which was first named as nuclear science. बाद में इसका नाम चेंज हुआ। Another big facility is we have a joint collaboration, which is this standard. Both of them are 20 graph generators. दोनों machines में कोई फर्क नहीं है. The only difference is that this machine is 14 unit double. 1 unit can take you up to 1 million volts, so 14 million volt potential, terminal potential can go, and ours is 15 unit. So there is difference of only 1 unit difference, 1 million volt difference. So they are actually, you can say, you have structured them or you have designed them for their needs according to what you want it to do. And there is a variable energy cyclone center, Kolkata, as you know, and this is a cyclotron, different sort of theory to illustrate the part. Next please. So how this idea came into picture, that how to bring all the universities under one roof. Hindustan is the bada hai, we have to work together and we have to look all the universities coming and performing experiments. And this idea came, and it was long back in 1968, and earlier on it was implemented in 80s to give this concept. And our late Prime Minister Mrs. Indira Gandhi signed this thing, and later on it came as a MSc in that year. Next. So construction started. So this जगह पे हमारा सेंटर वो उस समय barren island था like that. And then July 1986 that picture is. Next please. Structure started coming up. 86 we started erecting our tandem, but not horizontally, vertically. We are always making horizontally as well, but due to lack of space and other things, we have put it up. Next. So we can say December 87, one part was commissioned. Next. And then, by then more or less, the things were ready. Next please. So, some pictures from the commissioning. This is the top of the escalator tank. This is inside view of the tank. And now these are the potential rings. So UD unit, which I was talking about, is this one unit over here, which can hold a potential of 1 million volt. Next please. So this is the simple way of showing that how really it works. And you can see that this is a Van de Graaff generator. The commercial name is Pelletron. Why Pelletron? Because this charging of chain is made out of pellets. The company also sells Ladatron. The chain is like a ladder-like structure. So this is Pelletron commercial name. And you can see that there is an ion source, which is a negative ion source. So negative ions travels from there to this high terminal where we are sitting at 15 million volt. Negative ions attracted towards the positive terminal. There you strip off the electrons. What happens when you strip off the electrons? It will become positively charged. And then it is repelled by that positive charge. You can see here. Negative, and after stripping, positive, and then it is repelled. There you do the mass selection, and here you do the anion selection. Formula is very simple. E is equal to Q plus 1 into V. Where E is the energy of the beam, Q is the charge state, and V is the terminal potential to machine is sitting at. आप सिंपल कैलकुलेशन कर सकते हैं. 16 ऑक्सीजन 1608. How many number of electrons? 8. Maximum charge state 8. Probable क्या होगी? 5 या 6. Maximum probability निकालेंगे तो बीच वाला ही नंबर आएगा ना. तो सब कैलकुलेट कर सकते हैं. Next slide please. Okay. We cut it down. The cross section is here. There are certain things that how high is the tank, diameter, and what we can split from proton all the way to heavy ions like gold, and typical units are 5 to 50 nanometer. And these 5 things which you next please, these 5 things you see is the different experimental areas. Enter please. Yeah. So in the first phase we have these 6 beamlines which are dedicated to radiation biology, atomic physics, Fermion recoil accelerator, material science. GDS stands for the gamma detector array, and final particle scattering chamber. Next please. And this is the overall picture. Now, the picture which you saw, the first beam hall ends over here. Then we have beam hall 2, where the 0 degree line is dedicated to the linear accelerator, where you can accelerate the beam to much higher energies. And you can go to the higher regions to perform your nuclear structure or whatever material science or the other application studies. Next please. So you see, if we have only this structure, what I am trying to say that if you see this is mass, this is MeV per nucleon. As we go up with LINAC, we can go from 2 to almost quite high energy, and which is there. Coulomb array for very high energy Z's, and you can explore this good there. Next please. Okay, we are done with this. Next please. Next. Okay, this is the recent one. If we want to see it with the pieces, yeah, anyone. Oh, there are some numbers over here. So these modules are optimized to beta value of 0.08, and we read the beam, and then we go to the phase 2. Next please. So this is the picture for you that how effective the accelerator works. The small animation over here. Now देखिए ion source से ions निकल रहे हैं. There is an injector magnet where you select the mass. You can filter out. If you have 16 oxygen, other isotopes will also come. You can just select one of them. Then you strip it, and then analyze the magnet. You just take one charge and you can just switch it to your any beamline wherever you want to do the experiment. This example for the AMS part, which is done by one of my colleagues, is not written by me. Next please. So coming to the nuclear physics part, we have 3 big facilities. The first one you can see is a gamma array, where I belong to, and the group leader is Dr. S. Muralidhar. And the first phase was the single crystal germanium detectors with 12 detectors. As you can see on the left hand side, my left hand side. Okay. Now that is single HPD array, which is called gamma detector array. But then we have Indian National Gamma Array, which is made out of clover germanium detectors, much higher efficient. The overall efficiency of this array is 5%, and that is 0.05%. And we are somewhere in the world with this, because we can have 24 chromosomes in this array. 24 into 4 is 96 crystals. That is quite a lot. And we pull up with all the big facilities at India, TFR, so Kolkata, and we bring all the details together and try to perform the experiment. So that next big facility is required for separator. Just imagine a prism, sunlight comes in, split into 7 lights, and you have to select one of them of your interest. Something like that is required separator. So we have, in the first phase we have DIRA, Happy injection analyzer, and second phase we have hybrid recall mass analyzer. And this can work in vacuum as well as in gas mode for different applications. Coming to the last big facility is that we have an array of neutron detectors, which is made out of the liquid scintillators DC501. It's a very big array. You can come and see this place. Maybe some of you would have been here to see this. And another big facility is GPSC, which Dr. BPC, Professor BPC has already explained. This is one of the biggest facilities in the South Asia with a diameter of 1.5 meter. इसमें से rough vacuum डालने के आपको 10-12 मिनट वेट करना पड़ता है. And then the whole vacuum thing, as we said yesterday also, that if you break the vacuum, then you have to sit for hours to create it. That's why the IVF technology is in the picture. So what you do is that you get a vacuum, then you have a small slot over there. So what you do, you also fill this with vacuum, then you cut it off, so the vacuum is there, then you put your target up, get it? छोटा सा है, फिर आप इससे निकाल लीजिए. Then same way of inserting it. That is your idea. Next slide please. Okay, stop here. Now, you may be guessing that what exactly is Coulomb excitation, but before that you have to understand what is a fusion reaction. Fusion means target and projectile comes together, fuses, and makes a compound nucleus with very high excitation energy, and then it decays. As you can see in this now, you see, phase 1 will come now after this. Collision is there. Now we are joining it into two liquid drops. Compounding will form higher excitation energy, and then it will be followed by the decay. Alpha, electron, proton, neutron, and then quanta of gammas. Coming the gammas. Next please. But what happens at Coulomb excitation? There is no fusion between the one projectile and one target. Both of them have what? Fields. This electromagnetic interaction should only happen. And you see, when this electromagnetic interaction happens, both of them are excited. So only the decay is by the gamma, there is no particle emission at all, because there is no fusion at all there. Next please. Okay, so why Coulomb? Because it is one of the most powerful and the direct way of doing it. अगर आप फ्यूजन करते हैं तो आपको कंपाउंडिंग से मिलता है, फिर वो गामा में डीके करते करते ग्राउंड चले जाता है. लेकिन हम नीचे से 0% न्यूक्लियस को एक्साइट करते हैं और बिल्कुल प्योर वे में उसको स्टडी करते हैं. देयर इज नो ब्रांचिंग रेशो कमिंग फ्रॉम द टॉप और व्हाटएवर एंगल. सो वी आर जस्ट डूइंग फ्रॉम द बॉटम. So excitation mechanism is purely electromagnetic, and the nuclear properties involved are nothing but the matrix elements or the multiple movements. It's a modern independent way of doing it. What information brings to us is the static quadrupole movements. Static quadrupole movements आपके पास आएगी तो आपको पता लग जाएगा कि nuclear is of which shape, chromatic or an oblate. Next please. So, what is the function here? The function is an impact parameter. It depends that no nuclear part should come into the play. So for that there are certain rules which are made. This distance of closest approach should be greater than the radius of the projectile plus the radius of the target. Beam energy should be much less than the barrier, Coulomb barrier, because if you break the barrier, you go into the fusion, and all the scattering angles should be safe. Next please. So, there are different ways of doing it. अगर मैं उसको धीरे से धक्का मारूंगा तो थोड़ा हिलेगा, ज्यादा मारूंगा तो जोर से हिलेगा. तो हाउ मच यू हैव टू एक्साइट डिपेंड्स ऑन द एनर्जी ऑफ द प्रोजेक्टाइल. ज्यादा एनर्जी देंगे तो ज्यादा एक्साइटेशन होगा, कम देंगे तो कम होगा. So there are different orders here. See here, I is the initial state, IF is the final state. So if you excite, there is only one matrix element involved. We are considering only right now E1 nuclei. So there is E2, initial to final. Okay? First order, only one matrix element involved. You excite the nuclei from first order or initial state to final state. It takes only 10⁻⁻22 seconds to go. And the decay will take place around 10⁻⁻9 seconds. Next please. The second important thing is a parameter which is called the Sommerfeld. If you are doing a Coulomb excitation case, you would like to stay in a classical territory. If a quantum mechanical effect comes into picture, then you have to make a correction for it. And we don't want that. So that makes life very complicated. So the eta, which is given by this formula, should be much greater than 1. अब इस केस को लीजिए आप 58 nickel 120. To put the values, the eta comes out to be 127. So we are very much happy with that number. No quantum mechanics involved. Only classical things. Perfect Coulomb experiment can be done. Next please. Okay, next. This I have already explained. The first order. Then you can find out the V2 of 0 to stop. Second orientation is that if you just go little above energy, the second effect comes into picture. And is called the reorientation effect. Because this is only sensitive to the backward angles. Then you have a spreading of the second two plus plate in different angle. This reorientation part. But if you raise the range a little more higher, you can excite all the states and then maybe you have to more. अभी अगर नेक्स्ट रूम में एक ही बच्चा बैठा हुआ तो अपने बारे में सोचेगा, दो बैठेंगे बात करेंगे. और अगर बहुत सारे होंगे तो क्या होगा? तो सोचेगा, किसी को समझ में नहीं आएगा. So that is a bit complex more. Next. So what we can find out from this? What is the motivation of doing this Coulomb excitation? We can find the V2s. V2s से डरना नहीं है कि nothing but a transition probability from going from the ground state to the higher state. So people do other way around, doing the lifetimes, then calculating the V2. That is the indirect way of doing it. This is the direct way of doing it. You can always calculate V2 first, and then the lifetimes, or the lifetimes and then the V2s. So only the symbol which you will just see the differences is it's not there, but just the arrow up. Whenever you see an arrow up with V2, that is the coolest thing. If it is a down thing, that is the lifetime measured by fusion evaporation reaction. Okay, and then from the V2 or from the lifetime, you can easily calculate the water ball movement, and that will give you the shape of the nuclear, which is the nuclear structure. Next. So when it started long back, or it was initially done with very light beams. So when your beams are light, your beta is not very high. But they started doing it. Later on, they came to high Z projectiles. It made it much more popular, you can say. And now we are doing it much better germanium reactors and the particle reactors. Coulomb can only be done with germanium reactors. The first ever experiment which was done with particle gamma coincidence in India was my PhD thesis in India actually. I am discussed at my place. I will show you more details about it. Next please. Okay, we skip this because we have talked about this. Next. Okay, what will happen at when the projectile, or you can say, because there is no fusion, right? And the particle is moving. अगर moving particle में moving particle emit करता है कुछ तो क्या होगा? Doppler effect होगा. तो Doppler broadening होगी. उसको connect करना पड़ेगा. कैसे करेंगे? If you come to know the angles of where they are detected. So that we have some detectors. Next please. So stop. That's your target, which you can see, the arrow you can see is the beam. And then we have our detector, next placed around 17 centimeter away from that. This is called P-PAC, Parallel Plate Avalanche Counter. It's a gas detector, which is substandard at the angle of 15 to 45 degree. अब हमारे पास ये मैकेनिकल स्ट्रक्चर लिमिटेड है, तो हमें ये भी देखना है कि जो काइनेमेटिक्स है प्रोजेक्टाइल की और टारगेट की, काइनेमेटिक मींस यू आर डूइंग ए रिएक्शन and it will go away in some angles, but it should be directed in these angles, right? If it goes out of this, it will not be directed in this angle. You have to work out the kinematics according to your detector. Then what energy we have to keep that our particle and target, they are accepted in this part. Next please. And you know gammas are isotropic in nature and we can use them in the backward angles. Forward में भी लगा सकते हैं, but when this big reactor comes into picture and gamma rays are attenuated. If there is attenuation, we don't get the full strength of the gamma rays. So we have put 4 chromos in the backward angles. Next please. So this is P-PAC. You can see it has 2 things next, and this looks like that, 3 pieces. The first part is, next please, is a detector which is isolated from vacuum to entrance window because the other side is gas. Each side vacuum, each side with gas. And that is separated by very thin minor foil, you can see, 2 micrometer. You can imagine how thin it is. One has to be very, very careful while putting in the gas as well as the lighting. Next please. And then there are cathode segments, 360 degree, right? 16 segments, 360 divided by 16, 22.5. That is your each cake-like structure. So that is our resolution. You can go for higher things, but you make 36 segments as well. But then if you make 36 segments, that many more preamps, that many more electronics. So we are limited by that. We have to stand somewhere where we have that kind of money to do the experiments. Next, okay, and this is the anode one, okay, which is the concentric rings. And there are 150 rings, remember that. 150 rings means 150 detectors, 150 preamps. We cannot afford to have that. Next please. So what we have used next? We have used the delay lines, which is having a delay of only 2 nanoseconds, and by the difference, you can calculate the energy difference where exactly it has hit. So we have saved 150 preamps by just introducing this delay lines. Next. Okay, now coming to the setup, this is how it looks like. You can see these 4 germanium detectors which can detect the gammas in the backward direction. Inside this, because it's a closed array, inside this, next please, there is a detector which is sitting there, which is something like this. Professor Singh has also shown this picture. You can see for the 16 segments we have to take, these are the signals which are coming out of that. And this is this big table which you can see is nothing but the bias cable to the detector. And then there is gauge you can see, which is showing the gas pressure inside it, which has to be monitored every half an hour. When the gas goes off, the detector will blow. Next. अब बात करते हैं हम लोग पूरे इस एक्सपेरिमेंट जो हम लोगों ने परफॉर्म किया है, एक्सपेरिमेंट जो परफॉर्म किया. नेक्स्ट प्लीज. ओके, वी टॉक अबाउट tin. Tin, you know, is a doubly matching nuclear. Z is 50, right? And is 50, completely matching. Very hard to study, hard to break also. Next, but this is the whole chain. What is the isotope of this here? Now, all in the blacks are the stable ones. I hope you understand the stable ones, right? Which are there. And this is what we can study at our place. Now, also you must all know that tin is the longest isotopic chain with maximum number of stable isotopes, which are around 10 in number or something like that. So why we wanted to study it? I mean, it was a different kind of story, but before that, you have 132 tin on one side and 100 tin on one side, and you fill it from H11 by 2, or you can say from del T7 by 2 all the way to H11 by 2. Next please. And now, since it is doubly matching nuclei, so everything is paired, equally nuclei, and due to pairing, the ground state is completely compressed. What do you have to do in order to break it? Next please. Now they are aligned, you can say, and then you try to break this pair by putting the energy. Once you break this pair, next, then the angular momentum are aligned according to the breaking up. So these are the two particles. It can be two protons, this can be two neutrons. In this case, we have only neutron degree of freedom. Only neutrons are there. You can just test from 10, 100 to 132. There is only, because the other part is fixed, right? Z is 50, protons are 50, only there is 3 neutrons, no protons at all. So we are talking about breaking up of the neutrons. You break it next. So if you align your two angular models like that, next, that is how your 2 plus, 4 plus, 6 plus and 8 plus is generated, and which is directly proportional to the tangent of the theta. Next please. Another point that why we want to do it only by 2 legs. Because you see 6 plus, there is isomer sitting there. Isomer means high lifetimes. If I do that all the lifetimes below will be governed by that. Then I am in this, we cannot do it. The diagram of doing it is by the 2 legs. Next please. So this is the systematics, you can see. You see that 0 plus, 2 plus, 4 plus, they are almost in the single line. And as soon as you go to the doubly magic nuclei, this raises high, right? And the CDOT part which we talked about is that CDOT is nothing but the number of free particles. CDOT is 0 at the ground state, and then you break the pair, and CDOT is 2. Next please. Sorry. And if we look at the shell model calculators between two doubly magic nuclei, we should have a parabolic like structure. ये थ्योरी होती है. Next. Okay, stay here. Now, as I talked about that, before we did our experiment, picture was just like that. Now what you see here in this line, this black line, 90 zirconium core. 90 zirconium core is used in shell model calculations. Shell model calculations you can do by particle, but and you will get calculation तो ठीक है. एक को हमने पोटेंशियल मान लिया, certain core, and then you do the another free particles to do that. 19 zirconium core why I am showing, because it has both degree of freedoms, protons as well as neutrons. Okay, and 110 I will discuss just now, only neutron degree of freedoms. But if you see, both of them shows parabolic structure. And the one you see with the error bars are the experimental results. Before my experiment or before the experiment we performed. And you see, this till the mid shell, 116, it is following the trend of parabola. But as soon as you are going to the higher region, you have lot of, first of all, error bars, and it is jumping high. Why error bars are there? The answer is very simple, because they are not stable. They are unstable nuclei. When you do unstable nuclei means you have to go to RIBs, radioactive ion beams. They are very less intensities, much larger error bars. No doubt about it. But the trend is not as a parabola. And similarly, the last two stable isotopes in the black you see. Next please. Next. Here. These two were the nuclei of interest, which were having the error of almost 20%. 20% is too much. Today we can do a measurement with the precision of 3%. So if you get a ID, then we started and it was very available in the pain part. So our motivation was, yes, next. Does this 112, this is not visible here, sorry, but no, go back down. 112 and 114 follow the same trend, so want to do a precise measurement. So two experiments were performed, one at IUC and one at Germany. So IUC, this was the setup which I have shown you. You have taken the 15, it will be on the pin target at 175 MeV, and yeah, and at GSI it was the inverse kinematics. We have taken a thin beam on nickel target at a energy of 3.4 MeV per nucleon. Next. So these are the raw spectra. You can see broad peaks. अभी हमें क्या परफॉर्म करना पड़ेगा? of the correction. देखो आप कितना मोटे-मोटे आपको स्पेक्ट्रा दिख रहा है, right? Next slide please. Now you see after the Doppler correction. This is calculated for the pin, the top one, 0 to 2 plus, and this is calculated for the nickel. So how precise from this bit to this? That's why these indicators are required. Theta and phi information will be helpful to us in order to perform this Doppler correction. Next please. This was the experiment results from GSI where we could separate these two by the time of flight measurement, and you can see very clearly that 50 nickel is well separated from 114 and these are the 2%. The Doppler respect of 114 and 58 nickel. Next please. And then we came to do the determination of the V2s, that is by the double ratio method, and then we got a precision of almost 3%. You can calculate it yourself. Very simple way of doing it is this is the error bar and this is the number which you have got. How to calculate it? When you have these 3 digits, 0.008 divided by 0.242. Can somebody tell me? Do it in your calculator please. And show me what is that. You multiply by 100. How much is the precision? 0.008 divided by 0.242 multiplied by 100. Yes. Someone. 3.3% precision. 20% is 3.3%. That is the way of calculating it. Next please. Okay. अब ये पिक्चर थी हमारे एक्सपेरिमेंट से पहले. That is replace this number now with our results. Okay, next. Here we go. You see. We have reduced the error bars, but the trend remains the same. I mean, the bump is there after the mid shelf, it is rising up, it is not falling. Now, what can be the reason behind it? I mean, we have to look for it. Next, please. Then we look at the, and also there is another calculation which is called RQRP, relativistic quasi-particle random phase transformation, which doesn't consider any tone or anything. You do different sort of things and they very well match big satisfactory results they are given for the nickel and the ladder circles. But when we look at the label scheme of this, when we see the band crossing, यहाँ देखिए 116 तक आपका नंबर नॉर्मल से कोई बैंड क्रॉसिंग नहीं है, लेकिन इसके बाद में बैंड क्रॉसिंग है और वहीं पे आपको भी पूरा जंप होता है. So that can be a reason for this, but I'm not sure because I'm not sure detail. Next. So we finish 112, 120 and then इसके बाद तो कुछ काम करना पड़ेगा. So we move to 122. Next. Yeah. So this was the thesis work of Dr. Mansi Saxena. Unfortunately, she is my wife also.
सर आप ऐसे ट्रेन से मत बोलो.
रिकॉर्डिंग है.
मैं मेरे बच्चों को बहुत इंस्पिरेशन देता हूँ बीवी को कैसे देखना चाहिए.
Okay, next. So the main motivation to do this is that if you see this structure over here and these 3 nuclei were of interest, and this shows a clearly vibration-like structure. As you are aware that if you just take the E4 to E2 ratio, you will easily tell that what is the structure of nuclei. Here it is in front of you. If you just E4 to E2 ratio, nuclei are very much vibrational nature. Next. And also the label scheme completely shows. The labels are very evenly placed, right? So it's a vibration structure. But when we look into the experimental nuclei, 118 pin unstable nuclei. And this drops directly down here, and that last stable nuclei was having a very large error bar. Oh, thank you. After a long time. So the one read. Okay, here.
Thank you.
Okay, so this was an unstable 118, and this was the last stable which was having very large error bar. This is GOA ECM calculations, which are only theoretical calculations which are available for this. So we plan to do 120. Next week. And then if a nuclei is spherical in nature, the order total is going to be 0. So But the terminal has sizable profitable movement theoretically as well as experimentally. Next please. And there was a difference of almost 60% of this. Next. And then next, this was something like 36 single particle unit, so which motivated us to do this 120 trillion using the double ratio method. Next. And then same setup was used, so I will not show that. And we could achieve अब अपने आप पहले कैलकुलेट कर सकते हो मैंने फॉर्मूला बता दिया था we were there and it was coming after the physical review matter and it the result showed a different kind of behavior because rotational behavior, not the vibration. So it really opened up a new query about the Trillium. Next. So after switching 10, next, after going to Trillium, next, we thought we should explore a little more into this and then go into basic. Next please. And this is one of my students, as Professor Singh has also mentioned, Dr. Sunil Dutt now, and he's from, sorry I am not his guide, I am his student. By mistake it is there, the main guide is Professor Rizvi actually. And the mentor is our collaborator from Warsaw, as well as from GSI. And it is the probing of 122 billion. Next please. Next please. Next slide. Yeah. Anyway, before this. Yeah. So what was the reason that you want to study this region? Because this was neither spherical, not so much uniform. This was a transitional region. I mean, E4 into ratio was in between 2.2, you can say, to almost 3.2. This was the area of interest. Next. And this is how the different fields, you see the fields over here, and the axis symmetric deformation is up here, and AT2 line, and variable going over here, which is completely the direction deformation. Next please. The initial results which were performed, and you can see that these were not elastic, was not clear fluids, and the gamma lines which are over here are not very well shaped also, and they were having very bad illusion, and the numbers were very different, and the targets were not either. Next. So we performed this experiment using the same setup with the field nickel beam on the medium target. Next. And we got very good precise 2 plus, second 2 plus, and other states as well. Next. Okay, this is the next spectrum, close solutions and the other solutions. Next please. So what you think is that you see here, these are the theoretical values which very well matches each other. And the real part was the second 2 plus 6 which very well match and which was not there in the other reference. So what you take. Next please. And this one probably left us. Next please. Okay. Pins, next. Trillions, next. Variance. And then somebody challenged us about our 10 reference. Then came a lady next week, and then that brought us back next to the things once more. There was a lady called Andrea Yonklos from Spain, and she performed the D-SAM measurements for all these 3 lines, and she challenged our results. Next. So, these were our results in black, you see, and this lady came up with this new red colors. And this was a PLB, this is the letter B. And then we thought we have to take this challenge. We did a re-measurement. All this isotope constant. Next week. So challenge was accepted indirectly. I mean, not talking to her, and we performed the experiment with all these stable isotopes, and we got all the documented spectra. Always remember that whenever we are performing any full experiment, the setup should be absolutely same for the same only we should take the target. After reactor 8, second level 8 होता है, बिल्कुल नहीं हिलना चाहिए. Heat और fight का problem हो सकता है. Next, and you see here, 112, 618, 120, 122, 124. A single experiment performed all these isotopes, and then we came up next. These results slowly now. Next. Okay. These are the previous meter values, the Yonklos values, and our present results. Next. How they matched. theory, zirconium, core, tin core, R2 RPA. We should concentrate basically only on the zirconium and the tin core values. Let us forget about R2 RPA, but we need to matches up to a certain extent. Next. This was NNBC data, you can say nuclear data tables, and which almost is another Coolidge who perform experiment from US, Remington Coolidge. ये हमारे उन सब के results हैं next. और ये this was the results of that lady who challenged us in principle. Next. And then these are our present once more. We were still there. She deviated. व्यवस्था हुई. तो फिर हमने बताया कि नहीं है. There is no evidence of reduced activity out there, and we got and this paper was published and their physical review CSP. So the message we have sent to John, and we are closed by publishing this paper, and this will go really appreciated everywhere. Next. So now I think I've taken a lot of time of yours, and now we come to the summary part. So first of all, I talked about the tin and the 100 ton body tin, and the theoretical calculations followed by the Williams, which really shows the behavior of the soft triaxial nuclei. For the barium isotopes, we were very good agreement with a major value of 54.5 by Stokely. And the last part was the remeasurement, which we took the challenge from the DSAM, and we again proved that there was evidence of reduced activity. Okay, next. I'd like to thank Anna Stomas from Poland. She is a very good target maker, and I think one of the best in the world and she can do. And but really was online and so she made everyone very target for us. Next. So collaboration is important. I cannot perform the experiment on my own, so I need a team. So I have a very good team. This was my thesis experiment. And my German collaborator is here. My Guruji, Dr. Bhavik Saab is here. And my colleagues are here. And yeah, many more. This was the second experiment, the remeasurement over here, or the Williams, I think. Our colleague from German, but Japanese now, you can say. And another guy from I think Bulgaria or something. He's also here. Here is Mr. Smilda, here is the scholar. Next. And our government, go back. Our director man, Mr. Amit Jinger, he is a real expert of directors at IUC or everywhere. You can say he is doing very great job building these directors. Any kind of director you can contact on this gentleman. Next. So a few more things from few more experiments. These are the last experiment we performed. Yes. And thank you. Dhanyavad. Next. So this is it was great to be here. More on my YouTube channel, Roots of Life. Please do subscribe. Okay? I think I did it in my time. Thank you very much.
Yeah, questions please.
Can you measure higher order of movement higher order of movement
तो ये कैसे बोल सकते हैं कि इसमें कोलिजन नहीं हुआ है, इसमें सिर्फ वही दिया अच्छा हाँ
In future we are planning that so far all the experiments were done with the tandem, right? In the phase 1. Now the NAC is in operation. As soon as we are HCI, high current injector will be once high HCI is the 10 nanoampere can go up to 400 nanoamperes. Current will be high, beam time will be less, energy will be less. So now what we have the plan that we put a small CD detector. CD detector, understand? The pan you have seen, it's a very big detector, right? Now we reduce it by a factor of 20, like this. And we can put it in our Inga array in the backward end. And then we can really build that. Not only single step or much higher things. Yes. And anything else? Yes, Puneet.
Is there some advantage of using this reverse kinematic reaction, particularly for Coulomb excitation kind of studies?
Yeah. Otherwise, you cannot really differentiate. I mean, if you see look at the raw spectra, and later on you have the theta and phi function, then you correct it and you can really do the correction for the target excitation as well as for the critical excitation. And then once you do it for one thing, because there are four cases basically. Critical excited, one target this, there are 4 cases. And they have to match it to see the perfect part. So the resolution will go something like from 40 kV all the way to 7 kV or 6 kV, depending on the case. I mean, actually the aperture of the fluid nucleus. Opening angle, sorry. Opening angle of the fluid nucleus. Yes. Yeah.
The research you have done, how it can be beneficial for the society we can apply these results?
हमें पता लगा कि ये जो न्यूक्लियाई है ये इसका बिहेवियर क्या है सोसाइटी में तो हम तो इनका नहीं दे रहे भाई ठीक है ना वी हैव टू रिसर्च अबाउट द न्यूक्लियस स्ट्रक्चर ऑफ द न्यूक्लियस सो वी हैव टू अंडरस्टैंड फर्स्ट ऑफ ऑल दैट हाउ द होल थिंग इज गोइंग अप I mean we are going from the light ions all the way to heavy ions and how the structure is and what happens. It's not only that what happens. There is a ground state, but what happens when you are going high in the excitation and high spin also. That is our motive. Yeah, so what do you do? Coulomb excitation. Reason is that this is a model independent way. People used to do it with the lifetimes and other ways. So this is completely, there is no nuclear part involved in it as I told in the initial part. You are just having an electromagnetic interaction. You see, you are just exciting the nuclei. The nuclei gets excited on its own and then decays, and that is a direct way of doing it visually. Yeah.
Dr. Rakhalji, it was a nice talk. Can you please explain to the student what is the need of the Doppler correction you mentioned there?
Doppler correction.
From the point of view in that thing.
That will take a lot of time. So बाद में explain कर देता है.
आपको और एक टॉप दे दो.
I can give if you want.
Hello.
Okay then.
But then there is a detailed.
थोड़ा Coulomb correction very important.
Doppler correction.
Doppler correction is important. Yeah. Now that you cannot. See, if you have performed a Coulomb, then analysis is the main part, and there you go on. As I told you, there are 16 segments in the PPSC. Maybe all the 16 segments may not fire. Your particle is going in 1 or 2, and you have to look for those, right? And the scattering angle should be in the range as I told you. So what matters actually when you try to perform the Coulomb excitation? First of all, you will do a calculation of the cross section. Cross section है कि नहीं है? तो क्या काइनेमेटिक्स है हमारे मैकेनिकल स्ट्रक्चर के अनुसार है, फिजिबिलिटी देखनी है, फिर कितने घंटे का प्री टाइम देना है, बिकॉज इफ यू डोंट हैव एटलीस्ट 1000 काउंट under the peak, you cannot go to the precision of 3%. It can be 200 counts also. I perform my experiment, I show some result, but precision will not be that. So that all calculations have to be performed, and moreover over that the point of view. Because I am not in the committee who is going to decide whether my experiment is feasible or not. I am only going to present it. Right? That is it.
Thank you so much, Dr. Rakesh. It was a very detailed and wonderful talk. And thank you so much for putting so much effort to ensure that your talk comes down to the level of our students. Because many times otherwise people feel that they are आए लोग और अपने research का result दिखाया चले गए. But here of course, yeah.
What was the crowd like?
Yes.
I was talking to Manoj also that I would tune my talk now according to the people.
Thank you so much for your effort.
For that I have to put some time, but I hope I got something. That is important.
See, there is to be a time when
Thank you.
Always the first effort is, do I have enough to eat? Roti kapda makan. है कि नहीं? So if you see the scientists in the 18th and 19th century, they are all lords. Lord Kelvin. You understand what I am saying?
Only people who have a lot of money could really Lord Rutherford. Only those could do science. You understand? Science is something like art. Can everybody sit and start painting? No. It was the leisurely activity of the people who already had all the basic amenities of life. You understand? But this process always existed in man's mind. Where am I coming from? What is it? What is this nature all about? What is this universe? सबको लगता है ना? Right in LKG, UKG, you are taught twinkle twinkle little star. How I wonder what you are. आज हमारे वंडर कहाँ तक पहुँच जाती? हमें लाइट जो है लाइट ईयर से आता है. You know what is a light year? So we understand the star, we understand the sun. What do I do with it? That is not the question of the scientist. The question of the scientist is what is it? Exciting, right? After that, engineering came and you have a lot of suvidha and all that. That is job of scientist. No, it's job of engineers. You get your mind what I am saying?
Yes, sir.
Yeah. Today, आम आदमी को मौका मिल रहा है भाई, पैसा हम देंगे, आप जाके रिसर्च करो, पता करो क्या है. हमारा सुरेश है यहाँ, डॉक्टर सुरेश आ दीजिए. See, he is talking about something what is happening in black holes. Right? We are paying him from last 10 years. Go, find out. What a great joy. एक आदमी को आनंद मिलने के लिए हम सब मिलके टैक्सपेयर मनी है ना, हम सब मिलके पैसे दे रहे हैं, ठीक है ना? तो it is our job as scientists to tell the politicians, boss, we need to do this. You understand? We should not be guided by them. We should be guiding them. मैं कब एक चीज बताता हूँ आप सबको ना, इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम मेरे को दे दो, दे सकते हो? लाखों करोड़ों का घोटाला हो गया उसके ऊपर. Lakhs of crores, they sell the spectrum. Who sell the spectrum? The politicians. Do they know anything about the electromagnetic spectrum?
I hope you are not being recorded.
That's definitely recorded. Scientist का यही तो फायदा है, वो ट्रूथ बोलता है. डरेंगे तो ट्रूथ कहाँ से बता सकते हैं आप?
I was outside and just listened that someone else were talking.
No.
But here
Truth means that is the purpose of science. Science is to find out truth. And जो सच बोलता है वो कभी डरते नहीं. ठीक है, जाते तो डरते नहीं. जो बोल रहा सच बोल रहा हूँ भाई. हाँ, हम भी नहीं डरते हैं. ठीक है ना? अरे यार, अभी जो लोग सच बोले उनको फांसी भी लगा दिया ना, हीलियोसेंट्रिक सच बोला करके. लेकिन आज आप उसको एक्सेप्ट करते कि नहीं करते? You understand? हाँ, तो लोग जब सच बोलते हैं उसको फांसी भी चढ़ा देते हैं. ऐसा कुछ नहीं कि नहीं चढ़ानी, लेकिन हम डरते हैं उससे, नहीं डरेंगे. ठीक है ना?
फांसी से डरते हैं.
हाँ,
फांसी से तो डरते हैं.
आप डरते हैं, हम नहीं डरते.
एक क्वेश्चन उन्होंने पूछा था, इसका सोसाइटल बेनिफिट क्या है? You see, when you do all these kind of scientific work, you develop many instruments, many technologies are developed, which ultimately lead to the societal benefit. Like detector का डेवलपमेंट करना आपको, तो it will lead to the smoke detectors. कहीं आग लगाएगी तो आप smoke detector से
हम रेशम लगाते हैं ना स्मोक डिटेक्टर में. अब मेडिकल यूजेस तो बहुत सारे हैं. If you find new, you know, but that's not the purpose of science. That's what I'm saying.
try him as a chairman with Alusal explain.
The purpose of science is, yeah. This is what actually, you know, sometimes I keep wondering. We are the ones who know the electromagnetic spectrum, and somebody else is selling it. Who doesn't know anything about it? And without knowing the electromagnetic spectrum, do you have all these devices to it? Okay. But is it our purpose to prepare these devices? Nahi. The purpose of a university is not to create job seekers. The purpose of university is to create new thought process, original research.
Whatever instrumentation has come out later on for the application part of it has come from.
हाँ, because see, you have to be convinced. इसलिए बता रहा हूँ, ये नहीं कि मेरे को किसी से नफरत है या किसी से. I don't have anything. That's what is a scientist. A scientist, once he comes to know the truth, he knows that everyone is same. Same life principle exists in everyone. Does it change? It doesn't change. Therefore, if you are really educated, will you go and fight on the basis of religion, caste, region, language and all this? If you fight, then you are not educated. क्या सर? इससे ज्यादा फायदा क्या चाहिए आपको साइंस से?
अगर आप पढ़े लिखे गवार हैं तो वो भी कर सकते हैं.
हाँ. If after learning everything and knowing the truth, that what is it actually, is there in this world is oneness. And then if you start going and fighting in society, then what for the education is? So the greatest benefit to society from education is, we teach you the truth. We teach you that all of us are one. It's the same life principle which exists in everyone. Shastra में बार-बार बोलते ना ये, आत्मतत्व एक ही है. This is the truth. धर्म क्या होता है? धर्म is not religion. Dharma is righteous conduct. The conduct is he is also God, I am also God. So can I simply do whatever I want? Can he do whatever he wants? Both are God, na? My freedom ends where his freedom begins. That's all is Dharma. That's all is. Religion is the practice of spirituality. And spirituality is knowing the truth. And one of the process of knowing the truth is science. Okay? Please be clear, my dear men and women. Very, very important.
देखो सर आए.
So science का main purpose है such journey. Okay, now we are on to the next topic. आ रहे हैं 2 मिनट में आ रहे हैं. अभी राजगुप्ता जी का टॉक शुरू कर.
उनके टॉक के लिए
2 मिनट दीजिए हमें. Okay, प्रोफेसर राजगुप्ता.
नहीं आए सर अभी.
हाँ, राजकुमार गुप्ता जी. और राजकुमार गुप्ता ऐसे होते हैं. Are you there? I think I heard on online.
Yes, online तो है सर.
First, whether you are seeing someone there.
11:45. Should be seen there. सर राजकुमार गुप्ता जी को इंट्रोड्यूस करके शुरू करवा देंगे. अभी 11:45 राजगुप्ता हमारा प्रॉपर यूनिवर्सिटी का.
आए हैं यहाँ जो है राजकुमार
राजकुमार इतना ज्यादा क्या बोल रहे हैं. हमारा न्यूक्लियर रिसिस्ट है. अभी आता हूँ. थैंक यू सो मच सर. ऑनलाइन वेरी वेरी आप प्रिंट देख सकते हैं लेकिन आप प्रिंट करना
क्या हो गया उसको? प्रिंट के बाद प्रिंट क्यों नहीं हो रहा?
ओके.
दूसरा प्रिंट क्यों नहीं हो रहा?
इसका हो जाएगा.
ये ले जाओ.
हाँ भेज दिया मैंने. इसको भी अभी आप देखो इसमें आए नहीं आए.
अभी आप
इसको समझो भी ना. पहले उनके टॉक को देखो. देखो आए सर आए. उसमें जाओ मोर में जाओ 16 जो 14 पीपल है वहाँ. चल नीचे करो. राजकुमार गुप्ता वहाँ है तो. रुको अभी आएंगे.
Sure, sure.
Terrible few days health-wise. I go to hotel and just sleep. That's it. But then I come back and sleep here. Other than coffee. I don't even eat supper these days. Just go to but there's some tea hours. 6 or 5.
कब है? आए नहीं सर. नहीं नहीं यार.
चलो थोड़ा 5 मिनट रेस्ट लेके आ जाओ.
फिर सर वो छोड़ के आते हैं.
आप जाके अभी यार मैं राजगुप्ता जी को फोन कर लेता हूँ. एक्चुअली there's some confusion ना because उनको भी पहले होनी थी. हाँ सर थैंक यू. आपको राकेश जी कहाँ चले गए? वो राकेश को एक बार बुला दो. बड़ा मैंने भूल गए. भूल जाते हैं.
फोन लेना फोटो लेना
कैप पहनवा दीजिए।
हाँ वही बोल रहा हूँ मैं, भूल गया भाई, फोटो ले लो यार।
कैप पहनवा दीजिए। सही तरह से
This is why someone didn't have it. There will be a sound. There will be a sound in
Okay, I think Rajkumar Gupta sir is on available on.
आए थे भी,
आगे सर,
आ
आगे।
गए मेरे घर
We could give him this one. Raj sir.
Yes, sir.
Can you show your presentation? So, we just finished our tea and snacks and had a wonderful presentation by Dr. Rakesh. Gives me great pleasure to introduce to all of you Dr. Raj K. Gupta. He is currently an associate professor in Thapar University and has been associated with us in the last 3 conferences as well. Thanks a lot for your time and sharing your knowledge. He also is an expert in cluster decay model and dynamical cluster decay model, should I say, right? And we have also a lot of talks in this particular field. So with all his expertise, we hope that he will share his latest research with all of us. Dr. Raj Gupta.
Thank you, sir. Thank you, Professor Shastri, for giving me opportunity to present my work. I hope I am audible and my screen is visible.
Your screen is visible.
Okay.
Yeah, now you are audible as well. We have put you on the mic so that all the offline participants can listen to you.
Okay, sir.
Right. Thank you.
So, thank you, Professor Shastri. This time I am not coming with the collective clusterization model. So, we have started some new work as well.
Oh, excellent.
In collaboration with Professor S.K. Patra and Professor Nitin Jain. So, the title is Systematic Study of Fusion Barrier Characteristics and Corresponding Cross-sections using some medium-dependent effects in nucleon-nucleon interactions.
Very nice.
So, the talk is divided as follows: overview, then we'll discuss briefly about what is the medium-dependent effective nucleon-nucleon potential. Then we'll make application to fusion dynamics and study the barrier characteristics and corresponding cross-sections using different RMF parameters, and then I will. So, overview is the heavy, low energy, heavy ion reactions play an important role in exploring various aspects of nuclear physics. And for study of nuclear physics, we need interaction potential. And, it consists of Coulomb term, centrifugal part, and nuclear potential. So, and this is the essence for understanding the complex nuclear reaction dynamics. However, despite numerous theoretical efforts, the understanding of nuclear interaction in this total interaction potential is still confusing and it is not clear. So, in the present work, we are deriving this nuclear potential from the mean field approaches to study the heavy ion reactions. So, in this, the double folding approach furnished with the nuclear densities and effective nuclear-nucleon potential from mean field, relativistic mean field approaches has been used to study fusion as well as cluster decay in the past as well. So, this study aims to introduce in-medium effects, that is density-dependent terms in the nuclear-nucleon potential to study further. Now, as I have already discussed, the total potential consists of nuclear part, Coulomb part, and centrifugal part. Coulomb and centrifugal part are well known. Nuclear potential which is attractive and short range, this we have calculated using double folding approach, in which this is shown by this equation, in which we have used the densities of projectile and target multiplied by the nucleon interaction potential integrated over the entire space. Now this effective potential, nucleon potential in literature so far M3Y1, Michigan 3 GABA 1 is used commonly, and in R3Y recently we have developed the interaction potential which depends upon this coupling terms G omega, G O, G sigma, and cross coupling non-linear terms G2, G3, etc. And J00 is one ion exchange term. So as we see that M3Y is a phenomenological formula, whereas R3Y we use actual density dependent terms, in which we use density dependent using nucleon-Meson coupling within our relativistic Hartree-Fock-Gottlieb approach. Whereas in M3Y, this weighted density function is used for including the density dependent part. In the RHP relativistic Hartree-Fock-Gottlieb formalism, to include medium effects, we have used these equations. The constants GIs are multiplied by the functions, and the GO term, these are also multiplied by the another exponential functions. We have taken these equations from these references, and further the density dependent R3Y nucleon potential in terms of density dependent meson-nucleon coupling constants, they are written like this. So recently we have published a paper in Physical Review, and in which we have found this equation that these G1, G2 or G omega, G sigma, they are not just constant, they are depending upon the densities of projectile and target. So this is how we are including the in-medium effects in the nucleon-nucleon interaction potential. Now we have tried to see how the effective nucleon-nucleon potential looks for the different parameter sets, DDME1 at saturation density, ME2 at saturation density, NL3 star, NL3 star with G2, G3 term 0, and other parameter set along with the M3Y parameters, M3Y potential for the sake of comparison. And we see that the NL3 star with zero non-linear coupling terms G2 and G3, they are giving the most attractive B effective part, and NL3 star is or NL3, they are in between these variations. Then we discussed about the frozen and relaxed density approximation, which are commonly used in literature for studying for adding the densities of composite system, in which projectile and target they are coming close to each other. And we see that this frozen density approximation, the red one, when density is plotted as a function of r by 2, the internucleon separation distance. So we see that this frozen density approximation at the center, we overestimate the saturation density by a factor of 2. So recently Denisov has given the another way of adding the densities, that is the relaxed density approximation, in which the projectile and target get enough time to get relaxed, so that their saturation density comes down to the rho naught. And correspondingly, we try to plot the nuclear potential for frozen density with the red line, and relaxed density, which is the black line, and DDM3Y-1 and DDR3Y. DDR3Y is density dependent R3Y potential, which we have used now. And we see that this black line, which is DDR3Y, relaxed density approximation, is close to the DDR3Y, in which the density dependency on medium effects are coming in a self-consistent way. They are close to each other. So we see that relaxed density is more appropriate as compared to frozen density. However, frozen density has a limitation that it is used when projectile and target they are assumed to be frozen at a particular distance. Then we have tried to make the application to study the fusion dynamics of these interaction terms. And in order to obtain the nuclear potential using DDR3Y and potential, neither frozen or relaxed density approximation is used. We made it clear, we have used the in-medium effects self-consistently in the form of equations. And the medium dependence is introduced in both the projectile and target density dependent nucleon-Meson couplings. Then the results are compared with the R3Y nucleon potential obtained for non-linear NL3 star. This is commonly used parameter set in relativistic field approaches, and the TM1 parameter set as well. with the non-relativistic M3Y and DD-M3Y nuclear potentials. These, I have shown these total potential for illustrative case of calcium and lead. The other reactions will also show the similar effects. Here we observe that the R3Y NL3 nuclear potential gives the lowest barrier, this one, lowest barrier, whereas DD-M3Y TM1, DD-M3Y means the nuclear potential is of density dependent M3Y and parameter sets are TM1. It provides highest fusion barrier and corresponding cross-section will reverse. The inclusion of density dependence in effective nuclear potential increases the fusion barrier, obviously, because the in-medium effects results in more repulsive nuclear potential. So, in a nutshell, the effect of in-medium effects or to include the density dependence is giving us that higher fusion barrier, which results in lowering of cross-section. The comparison of fusion barrier characteristic and fusion or capture cross-section obtained using different form of nuclear potential, that is using R3Y, DD-R3Y, M3Y and DD-M3Y, is carried out for the 6 reactions. Namely, these reactions are leading to formation of light, heavy and superheavy compartment. So we have tested these approximations in different mass region of light, heavy and superheavy compartment. We are finding the similar observations. So this table shows the variation of the numbers for barrier height and barrier position for different NN potential and parameter set for the classical reactions. Now then we further try to find the cross-section using the well-known Alson-Baum formula, in which cross-section is given by pi by k square, where plus 1, and BL is the transmission probability, which is calculated under the approximation of inverted harmonic oscillator, or it is commonly known as Higg-Wheeler approximation in Baum formula. Then we calculated the cross-section for the potential we have obtained for the said reactions, and we found that fusion cross-section obtained within the different RMF potential, the R3Y Newton potential as well as nuclear density obtained for NL3 parameter set are observed to give a comparatively better fit to the experimental data than the other nuclear potential. So we are finding that R3Y NN potential is superior in some way to the other considered choices of NN potential or parameters. So further, this is the first half of the talk. So I am concluding first half, then we will move on to the systematic study. It is observed that the inclusion of density dependence in effective NN potential increases the fusion value, which leads to lowering of fusion cross-section. Further, DD-M3Y NN potential underestimate the cross-section, whereas relativistic R3Y NN potential and nuclear density obtained from NL3 star parameter set are observed to provide comparatively better fit to the experimental data. Obviously, density, if R3Y is close to experimental data and if you try to include in-medium effect, it will lower the cross-section. So, other structural effects will also contribute, which we will study in our subsequent studies. So, further, the DD-R3Y NN potential obtained using lax density approximation is observed to give reasonable match with that obtained in terms of both projectile and target density depending nuclear mechanism properties. A systematic, and then we will try to find the systematic study of fusion barrier characteristic obtained using different atomic density distribution, relativistic R3Y, DD-R3Y, non-relativistic M3Y and NN potential for around 24 near fusion reactions. And the choice of reaction is based on that the isoscene asymmetric, they are isoscene asymmetric reactions and they are forming heavy and super nuclei. Now, before moving on to the study, let us see the comparison, how we are making the comparison, how it is worked out. Comparison of different RMF parameters. As I have shown already, the folding equation, it consists of two parts. First one, we have the densities for projectile and target, and second one, we have the NN potential for nuclear potential. So we are obtaining the densities from RMF using the NL1, NL3, TM1 and DD-ME2 parameter sets. So this is the one part. Then we have obtained the E effective, which is the effective nuclear potential. We are obtaining it via M3Y, the phonological formula, and from R3Y as well. And further with R3Y, since this is a density dependent part, so we are also using the similar parameter sets as that of densities to obtain the V effective from R3Y. And the choice of reaction, the reactions are mentioned here in this table, and approximately N by Z ratio is up to 1.5 or 1.55, high N by Z ratio. So for these 24 reactions, I have shown the variation of barrier height and barrier position with respect to the bus barrier. Since bus barrier is very commonly used by the nuclear physicists around the world, so we have taken the reference point as bus barrier, and we show that how these VB and RB, they vary with respect to the bus barrier for different parameter sets. So we find that that VB lies in the range of plus minus 5% of deviation, and RB is approximately is on the positive side, which is approximately 7 to 8% variation with respect to the bus characteristic, bus parameters. Corresponding cross-section for these directions are shown here, and I have listed the observations that the RCY and DD-RCY interaction potential give much better overlap with the experimental data as compared to the phenomenological M3Y. The DD-ME2 parameter set gives the lowest, whereas the NL1 set gives the highest cross-section value for given systems. Out of NL3 and DM1 and DD-ME2 parameter set, NL3 is observed to fit the experimental data better. The TM1 parameter sets with self-coupling terms of omega meters. So it gives a repulsive NM interaction. So this leads to not match with the experimental data. Now then we want to study the effect of NM potential and RMF density parameters. So what we have done, we have fixed the densities using NL1 parameter sets and fixing the NM potential, that is V effective. Using first we use NL1 parameter set, then we use NL3. So we have two variables, density and effective nuclear potential. So if we have to see the effect of individual one, then we have to keep first one constant and vary the second one. Then we will keep varying first one by keeping the second one constant. So this is what we are doing in order to see the effect of densities and NM potential on barrier characteristics in fusion section. So first we are fixing the relativistic RC by NM potential. The first one in these figures, it shows NL1, NL1 and NL3. So and varying the density. So now we are varying the projectile and target density, and we are obtaining them from different parameters. And we see that the NL3 TM1 signifies RCY NM interaction potential obtained for NL3 parameter set, and is folded with RMF density distribution which are obtained for TM1 parameter set. So this terminology signifies first one for effective potential and second one for density parameters. Out of 8 possible nuclear potentials, the one with TM1, NL3 and NL1 give the highest and lowest fusion barrier respectively. So this is the observation, and it can be inferred from this that small increase in density of fusion nuclei at surface region or the tail region lowers the barrier height by approximately 1 MeV, and this 1 MeV is quite significantly at the below barrier energies, at which the section varies drastically. This slide shows the comparison of cross-section as a function of center of mass, and here we see that TM1 density distribution decreased the cross-section, whereas NL1 density increased the fusion cross-section. Also, the difference from the cross-section obtained from different nuclear potential becomes more prominent as we increase the mass number of the projectile. So it varies with the mass number of projectile as well. Then secondly, what we are doing, fixing the density and varying the NM potential. In first part we have shown fixing the NM potential and varying the density. Now we are reversing it. So this shows that modification in the fusion barrier characteristic caused by changing in effective NM potential. So this is the total potential versus R graph for the considered reactions, 3 considered reactions. And we see that if we change NM potential, then the change is comparatively more significant than one observed by changing the density distribution. So NM potential is playing a significant role. And the barrier height increases by up to 5 MeV on replacing RCY NM potential obtained for TM1 parameter set with the TD, the density dependent RCY NM potential obtained for TD-ME2 parameter set using the RD, relaxed density approximation. So if a role of V effective and the in medium effects are quite significant in the study of fusion. Then corresponding intersections are shown. Here the highest intersection is noted for the combination of NL1 and NL1, whereas the lowest intersection is observed for DDME2 and NL3 parameter sets. The inclusion of in-medium effects in microscopic NM potential decreases intersection, and the structure effect of interaction potential are observed to diminish at energies greater than the fusion barrier. Obviously, the nuclear structure effects are more prominent at below barrier energies, and at above barrier energies we have the centrifugal potential, which is dominating. So finally, in the conclusions we have, on the basis of calculation result, it is concluded R3Y NM interaction potential is a relatively better fit to the experimental data than M3Y1. The nuclear density and the R3Y NM potential obtained for RMF parameters at DDM1 give comparatively repulsive nuclear potential and consequently increase the fusion or capture cross-section. All these observations prove that inclusion of vector self-coupling down in R3Y NM potential increases the magnitude of repulsive core, which consequently underestimates the cross-sections. The DTR3Y NM potential calculated for DDME2 parameter set is observed with higher barrier height and lower fusion cross-section as compared to the in-medium independent R3Y NM potential obtained for NL1, NL3 and DDME parameters. Both the densities and R3Y NM potential obtained for NL1 parameter or NL3 parameter set give comparatively better fit to the experimental data than the other considered parameter set. So which one is to be chosen the better? Because both are giving the comparatively better or equal results than L1 and L3. So if we consider the overall description of bulk properties and fusion characteristics of finite nuclei and property of infinite nuclear matter, we see that somehow NL3 is seen observed to be superior to NL1, though they are giving similar results in fusion, but the background of NL3 is more successful. So the winner is NL3 and is becoming favorite choice across value of fusion in products in frequencies. So thank you.
Thank you very much. Excellent introduction to the new work which you are doing. I'm not Shastri just stepped outside, so I'm feeling for this couple of seconds. And now last audience, any questions for Gupta, please? Theoreticians in the house, audience. Any questions? Yep, go ahead. This doesn't discuss, very good.
So, okay, Dr. Muhammad Imran has started.
No, we're just thanking the
questions. Okay.
That Rajkumar, we're thanking him.
I just went to see them.
Yeah, please continue to thank you.
Thank you, Dr. Rajkumar.
Thank you.
Sorry, I just had to go down to see the other invited speakers who have come offline. So, thank you so much for your time. And any questions?
I asked him.
No? Okay. Kindly share your slides with us so that we can share it with the students also.
Okay, sir.
Right. Thank you. Okay, next we have in the schedule Muhammad Imran.
Yep.
Yeah, he is already online. Okay.
Alright.
Good morning, Dr. Muhammad Imran. We can't hear you. You might have to slightly increase your volume. आप बताएंगे?
The new first skin thickness of what the 284 which?
Serum cell is not talking.
अर्जेंसी आ गया था,
इसीलिए मैंने इसको डिस्टर्ब नहीं किया। मेरे पास आधा घंटा का लीव है।
हाँ चलो good thing. They're gone?
Just
yeah, introduce.
Now I would like to invite Dr. Muhammad Imran, who has test faculty in the Aligarh Muslim University, and his research area is theoretical nuclear physics with strangeness, super heavy nuclei, study of neutron stars and nuclear astrophysics. he has done his BSc Honours in Physics and MSc Physics from Aligarh Muslim University, and also obtained PhD degree in the Theoretical Nuclear Physics from Aligarh Muslim University, and currently he is guest faculty in Aligarh Muslim University. So I invite sir you to give your valuable talk. So you are not audible.
हमारे ऑडियो बंद है.
We can't hear you, sir.
Hello, sir. Am I audible?
Yes,
Yes,
now
sir.
you are.
Yes, sir.
Kindly share your screen and start.
Am I audible, sir?
Yes, sir. Yes, sir.
So wait a minute. So I'm connecting.
We are not able to hear you, sir.
Might not be problem. We can't hear you. In between we could get you, but now again we are not able to hear.
So, stay in the hotel. Then sleep.
सर हेडफोन निकाल के करना है मेन वाले से.
Thank you. Because I learn of it in the morning.
Now am I audible?
Yes, absolutely.
Right.
Start.
Yeah, so,
I came.
thank you, sir. Good morning to all of you. And
sir, tell me
at the very
something
outset,
you
I would
get
like to thank the organizer of this conference
Exactly.
provide me an opportunity
And then
to present my work. And it gives me immense pleasure to be a part of this conference because I am associated with the same department from where Professor H.S. Hans obtained his PhD and started his career. So as we all know that this conference is basically organized as a part of the centenary birth celebrations of the Professor H.S. Hans, and he also associated with the same department from where I am currently working. So it's a very proud moment for me. So I am going to present my work. The topic of my presentation is neutron skin thickness of omniscient isotopes having the mass length between 270 to 300 within the relativistic mean field theory. So first of all, I will introduce about the historical perspective of the history of the nuclear physics. Then I will come to the theoretical aspect of nuclear physics. Then I will briefly describe the relativistic mean field formula. Then I will show my results and followed by the conclusion. So, research on the nuclei was started after the alpha scattering experiment in 1909 by Peter and E. Marsden, suggesting that all the mass is concentrated in a very small place, in a small volume, and it is positively charged. And that is, as we all know that famous alpha scattering experiment. So, from this year 1909, the nucleus comes into existence, and and a lot of work after this alpha scattering experiment is done. But till now, particle stable predicted nuclei are nearly 8,000, from which nearly 209,32 are experimentally observed, out of which 373 are even and 469 are odd A, and nearly 726 are the odd A.
nuclei. As we know, the lightest experimental known nuclei is neutron, and heaviest experimentally known nuclei is Omnisom, which is discovered in year 2002 by American and Russian researcher at Okay, so here in this slide I have shown the nuclear landscape. As I told you, there are nearly 8,000 predicted nuclei, over which nearly 3,000 are experimentally observed, and out of 3,000 experimentally observed nuclei, the total stable nuclei are nearly 251, even nuclei are 145, and even odd nuclei are 53, and odd even nuclei are 48, and odd nuclei just 5 nuclei are there. So in this nuclear chart, the stable nuclei are represented by black lines, and known nuclei are also stable known nuclei are represented by the red region, and there are some tripline regions, proton tripline and neutron triplines. And as we know that the deviation from NZ1 for lighter nuclei, the ratio of the N to Z should be 1. But as we know that as proton number increases, so Coulomb number increases. So to overcome this Coulomb repulsion, the NZ ratio or the non-unity NZ ratio necessary for the total stability of the nuclei, or we can say that we need more neutron required to overcome the Coulomb repulsion. So here in this slide I am going to describe some theoretical aspect of nuclear physics. The primary goal of the nuclear physics research is to understand what is the interaction between the constant particles of the nuclei. The constant particles are basically the nucleons. So various phenomenological descriptions or various phenomenological studies are conducted so far based on ab initio method to the realistic and potentials, and the annual potentials taken in the study earlier studies are Aragon, Argona, Hudson, Margon, Newman, Paris, etc. And as we know that the two-body ion interaction in vacuum is well constrained by experiment, but three-body processes are less, and also hypernucleon and nucleon and hydronucleon interactions are very less known to us. So to study the interaction between the nucleons or the constant particles of a nuclei, many body methods like Bethe-Fog and especially coupled Green's function, correlated function method, Bernoulli Monte Carlo method, Green function Monte Carlo method, and recently auxiliary field diffusion Monte Carlo methods are applied to study the properties of the nuclei. And another approach to study the nuclei are the QCD based or QCD inspired description, which basically derived from the QCD, Butterworth QCD and NGL background. And the latest one, or the widely accepted theory that satisfactorily explains the spectra of the ground state properties of nearly whole chart of the periodic table is the RMF theory, which basically originated from the field theoretical description derived from the Lagrangian density mean field approximation. It is also a phenomenological study of the nuclei. Various interaction parameters are fitted to the ground state properties of the nuclei. So here in this slide I am briefly explain what is the relativistic weak formula and how it is formulated. So basically the Lagrangian density of a nuclei within the relativistic mean field representation is given by the Lagrangian density, and Lagrangian density is incorporated, or Lagrangian density is containing nucleons interacting via the scalar and vector meson fields. The photon field is incorporated through mu in this expression. Okay, here in this expression we have represented the mass or coupling, and coupling between the nucleons, and the drug small is represented by the side. The field for the fast rho meson is denoted by rho, omega meson by b mu, and sigma meson by r to g mu. Here g s, g omega 0 are the coupling constant, and coupling constant for the electromagnetic interaction is e square by 4 pi, and that is equal to 1 by 137 are the and G2, G3 are the self-reflection coupling constant for the sigma field. So the Dirac equation for the nucleons is obtained by the classical variation principle, and in this equation we use the mass
modified mass of the nucleons and the vector potential that is basically responsible for the interaction of the nuclei. And as we see the mass, sorry. So the vector potential and masses of the nucleons are represented by this equation, which is I think visible to all of you, and the field equations for the mesons basically obtained from the variation field. These are the Clem quantity equation which is written here. The scalar and vector, the specialty of this formalism is that basically it provides the density for the scalar and vector fields. The scalar and vector field density can be computed by taking the logs of the fields. And finally, the area of the nucleons and nuclear matter are calculated from the formulas basically written here. The charge Arrhenius radii can be calculated using the standard expression, which is nothing but the square root of the expected value of the proton radius plus total particle radius. Okay, and another important property of the nuclei, that is the deformation. The particle deformation of the nucleus can be calculated as the sum of the particle movement of the neutron and proton, and it can be computed using this formula. The total energy of the nucleus in this formula can be calculated as the sum of the single particle energy plus the energies related to the fields and pair energy, or we have to take care of the pair energy and center of mass energy correction. The VCS pair is Arabic theory is basically given by these equation where we consider the constant gap for neutron and constant gap for the proton, and we calculate the pairing energy correlation, which is very important in description of the ground state properties of the nuclei. So we have taken the super heavy element of meson. Super heavy element usually defined as the chemical element with the atom number greater than 106. In the super heavy element, the strong Coulomb repulsion pushes the nucleons to large deformation and overcomes the surface tension that tries to keep the nucleus at small deformation. Ognisson, that is discovered in 2002 by Joint Institute for Nuclear Research, near Moscow, Russia, by a joint team of Russian and American scientists, and it's the newly discovered element is named by the scientist Yuri Ognisson, that is actively involved in the group. The R isotopes. So here are basically many isotopes related to this newly discovered Ognisson. All isotopes in the band of 378 to 360 mass number are predicted to have lifetime nearly 0.001 second to 1 second. Dominant decay modes in this chain are fission and beta emission. All the isotopes in the band of 360 to 330 are predicted to have lifetime 0.001 to 1 second. Dominant decay mode in this chain are fission and beta emission. The observed lifetime of 294. Ognisson is shorter than the predicted half-life of any isotopes between Ognisson 294 and Ognisson 290. Ognisson 281 was experimentally observed and have a half-life time of 0.7 millisecond. Actually, I have taken the range 276 to 300. But as we know that 281 is experimentally observed and have half-life of 0.7 microsecond. So before this 281 mass number, we have taken 6 isotopes which are very smaller lifetimes, and the possibility of these isotopes are not experimentally observed because lifetime is very short. But we have taken 6 isotopes also below the mass number 281 and see what and observe what kind of the parameters changes or what kind of the properties of these nuclei are expected by our theory. So we have calculated the binding energy per particle, deformation parameter, beta 2, charge radii, neutron proton radii, and we have basically focused on the neutron spin thickness for the said isotopic chain. Basically the isotopes taken from the mass number 276 to 300. And we have focused on the neutron skin thickness. That is nothing but the difference between the RMS radius and the beta deformation parameter. And as we observe that the deformation goes on decreasing when the mass number is increasing. And also the charge radius also goes on increasing. And suddenly at the mass number 26, the charge radius is dropped abruptly. And we have calculated the neutron radii, proton radii, and neutron radii, and then we have to basically focus on the neutron spin thickness. This is nothing but the difference of the radii of the neutron proton. As the neutron, and actually adding more number of neutrons to the nucleus create a contrast in the functionality of the neutrons or neutron and proton. This basically this may results in the decoupling of the neutron and proton member, and that basically responsible for the formation of the nuclear skin structure. So here we note that asymmetry parameter. With asymmetry parameter, that is the difference of n minus z by a, we have calculated. We have observed that as the asymmetry parameter increases, means as we are adding more neutrons to the nucleus, then the neutron skin thickness increases linearly. So here in this table again we have shown the ground state properties of the same isotope, and the same trend as discussed in the table 1 is also observed here. Here we have plotted the neutron number versus the neutron radii, and the vertical or basically we have plotted the charge radii for the considered isotopes, and we have observed the variation of the charge radii, and we note that at the neutron number 168 there is a sudden drop in the charge radii, and in the second figure we have plotted the neutron number versus the neutron skin thickness, and we observe that the neutron skin thickness increases when we increase the neutron number, and in the last figure we have basically plotted the asymmetry parameter. Asymmetry parameter is nothing but the variation, or asymmetry parameter is nothing but the difference of n minus z and divided by the whole atomic mass of the nucleus. It is basically the asymmetry parameter is related to how we add the neutrons to the nucleus and how this neutron skin is observed. Okay, here in this slide I am going to present the density distribution of the considered isotopes. And as we see here that the density distribution for some nuclei, center density distribution for some isotopes are prominent, and for some isotopes the center density distribution is not so prominent. So center density distribution basically results in a bubble structure formation. From our study we can say that some nuclei may have a bubble structure because the central density distribution is prominent, more prominent in some isotopes. So we have calculated the binding energy per particle, charge radii, neutron radii, proton radii, particle deformation parameter for the selected isotopes of ornithine, and we have compared our result to the FRDM model, and our calculated parameters are close agreement with the parameters available. As I told you earlier, the neutron skin thickness, that is very important property associated with nuclei, neutron nuclei. So in our study, neutron skin thickness is observed for all the considered isotopes of the element on this one. The neutron skin thickness increases gradually. The neutron number for the isotopes that as the neutron number increases in the isotopic chain, the neutron get themselves adjusted in such a way that maximum stability is imparted to the atomic nuclei, and we also observe a kink at the mass number 295. As the increasing neutron thickness beyond this isotope reveals that the neutron become less bound, thus giving rise to a large neutron thickness. We also analyze the variation of neutron skin thickness with the relative neutron axis and found a slight peak again at the mass number 295, which may be possible due to the realignment of neutrons towards the periphery in order to accommodate the proportion of other significant central density distribution. Or further, central density depletion is observed for all the isotopes, selected isotopes, which may be a cause of the bubble structure formation. So here I am going to conclude my work. We conducted a systematic study of the bulk properties, binding silicon particles, charge radii, neutron radii, proton radii, or particle deformation parameter, neutron thickness. For the selected isotopes of magnesium, we observed neutron thickness, skin thickness for all the isotopes, or vertical RMM study of the considered isotope useful inputs for carrying out the neutron skin thickness measurements and may also help in the synthesis of new neutron-rich isotopes in the near future. Thanks. Thanks a lot.
Any questions?
Sir, experimentally, how we measure thickness of neutron?
They'll come there. Come there.
Hello.
Hello.
Excuse me, sir. Experimentally, how we measure thickness of neutrons?
There are so many experiments. Actually, electron scattering experiment is there from where we can extract the neutron thickness.
Electron scattering for neutron skin measurement.
Electron scattering is a proton skin charge radius, not a neutron thickness.
Neutron skin thickness, sir.
Electron scattering goes to only charge radius. Not the neutron thickness.
It's okay. Afterwards, I will tell you.
Sir,
Please ask him.
Good.
Now you have a question.
That's good. Yeah, that's good.
Students are now slowly getting confidence.
Sir, I have a question regarding the decay mode. Sir, you mentioned that
Yeah, actually, sir, we are working on this problem. We are going to explore the decay modes. I am just start working in this field, so I am planning to also study the decay modes of this field.
the second question is about the definition parameter that you are using for quadrupole only. So, have you tried to use higher order of definition?
Yeah. Some people also work on this with the help of the available online course that is actually code in which they are studied the media in the triaxial radial form. In this case, they also explore the higher order of deformations.
Thanks.
Thanks a lot.
Thank you.
Simple question.
Now,
Sir, one more question.
Yeah, sir,
Sir, can you please tell me that how is the deformation parameter beta 2 related to the asymmetry? As you have shown in the slide that as the mass of the neutrons goes on increasing, the deformation also the deformation decreases. So can you please tell me why it is so? With the increase of
Deformation parameter related to symmetry energy. In various ways, some people work on this and they explore the effect of the surface part and wait a minute. The symmetry parameter actually the symmetry parameter that is the difference of as we added the more neutrons to the nucleus, so as I told you, this may result in this produce the contrast in the formation of the nucleus, and that leads to the decoupling of neutron and proton. So as the symmetry parameter increases, means the number of neutrons increases, that will result in the more Fermi contrast, so more decoupling between the neutron and proton matter, and that increases the neutron significance.
so that means the deformation must increase then, I think.
Yeah, deformation should also increase.
But in the table it is showing that the deformation is decreasing with the, yes, this one, that the deformation is decreasing with the
increase in
Deformation is not decreasing actually. We don't have very regular trend in the deformation. For 287 mass number, the deformation is 0.054 and for 288 is 0.02 and for 289 it is 0.002 and for 298 is 00. Means our study suggests that 298 is correctly symmetric. So there is no trend in the deformation parameter. No sad trend observed in the deformation parameter.
Okay. I think now we are in online. हो गया ना अभी? Next is oral presentation. Thank you, Dr. Imran.
Thank you so much.
Thank you. So we will now move to the next session. That's on oral presentations. And
There are a couple of more lectures, right?
no,
Okay, cancel?
that's cancelled.
Okay. Then I saw the list, there are a couple more.
Actually, he had some urgent.
Okay. That's fine. Just check.
1:30, I think we're supposed to start oral presentations.
Right, I know.
Yeah, little bit down, but I think
No, that's fine. That's fine. But what I'm saying is that okay, that the other pieces are cancelled.
yeah. So now we can start with oral presentation.
There are the other two guys.
They are going to join online.
Oh, they were done online. Okay, all right. So, but they're unlucky. I'm the only guy here, and then the other guys there. So, I want these guys. Tell me that much.
What did you say?
No, sir. All right. Good afternoon. Good afternoon. No. We have got 4 presentations this afternoon. We have section 3. Okay. First one is going to be Shikha Awasthi. Shikha, oh, you're already there. Thank you so much. Okay, and as you know that we did yesterday 10 minutes presentation and 5 minutes of question and answers. And the audience should ask all the questions to the presenter so that the presenter gets marks for that and they get awards because of that. Okay. If you don't ask questions, they don't get marks, they don't get presents or awards. So please ask questions. Please go ahead.
So good afternoon everyone. Today I am going to present my work on phase shifts for nuclear glucose skating using phase function method. So the contents of my presentation is the introduction part, methodology we are using, results and discussion, and then conclusion. About the introduction, we know that one of the most important topic in nuclear physics is the interaction between two nucleons, any two particles, mostly they are nucleons. And during these scattering processes, there are different distributions of the scattered particles. And from these distributions, the nature of interaction we can derive between those various particles. And these interactions will further lead to the knowledge of their inherent structure, or you can say about the stability of the nuclei. Now, the main objective of my work is actually to determine the phase shifts for 2s half states, that is ground state of neutron-proton and proton-neutron systems, by considering two body interactions. And the interaction potential I am using here is the Melfit-John potential. The phase shifts I am getting by using the phase function method, and the lab energies I am taking from 1 to 19 MeV. So since these lab energies I am taking are way beyond the threshold of 3 MeV, which is for both for neutron-neutron and proton-neutron system, so we have to account for imaginary phase shifts as well. In addition to the real phase shifts, we have to account for the imaginary phase shifts as well. Now the methodology of our work, it goes like this. We will define some theoretical model of interaction, then obtain the numerical solution by using some suitable numerical method, and then determining the phase shifts for this ground state, 2s half state of neutron-neutron and proton-neutron system. About the interaction potential we are taking, the Melfit-John potential, it is given by this formula minus VA e raised to power minus mu r upon r plus VR e raised to mu r upon r, where this minus VA is the attractive part and VR is the repulsive part of the potential. And we have the condition mu r, which is there in the exponential part. Mu r is equal to 2 mu a, and in the units per meter inverse. So by including this condition, we are making our potential as a 3-parameter potential, and it consists of both repulsive and attractive parts, so as to explain the nuclear interaction clearly. Now for proton-neutron system, we added Coulomb interaction as well, which is given by this Z1 Z2 square upon R, error function of beta R, where this Z1 Z2 is equal to 1 for PD system and E square is 1.44 MeV per me. Next, error function is defined by 2 by under root pi 0 to beta R exponential minus x square dx, and then beta is defined by under root 3 by 2 into RPD, where this RPD is equal to 1.9642 Fermi meter, is the root mean square radius of proton-neutron system, and by this putting this value, we'll get the value of beta as from this formula. We'll get it as 0.441 per meter inverse. Thus, the total interaction potential for proton-neutron system is given by Vr is equal to Vmt plus Coulomb interaction. So it can be done like this. This is the Coulomb part is this error function, and this is the main interaction potential, method jump potential. Next, since we are dealing with the energies more than the neutron breakup threshold, so Berylak suggested to add some imaginary part to this local potential. Here local potential, which we are using method jump potential, we added potential. It is just real plus imaginary part of the potential we are adding, and we'll obtain the imaginary phase shifts. The total interaction potential is then utilized in the phase function equation to obtain the scattering phase shifts. Now, what is the phase function method? Basically, the importance of phase function method is that we will obtain the scattering phase shifts without the use of any wave function, and we'll use only the interaction potential to obtain our scattering phase shifts. And next, another importance of phase function method is that we obtain the relation between phase shifts with respect to distance by this phase function method. Now, the phase function equation is a non-linear first order differential equation, and in terms of the Bessel function JL and Riccati Bessel function JL and Newman function eta L. It is given by delta L dash here, where is delta L dash means derivative of this phase shift equal to minus VR upon K is the interaction potential divided by the wave number and multiplied by the Riccati Bessel function and Newman functions. So we are taking the condition at like this: the wave function, our phase shift at r is equal to 0 should be equal to 0. So now this equation, this is the equation for Lth partial waves for L is equal to 0, because we are doing the calculations for S wave only, that is L equal to 0. For L is equal to 0, our Riccati Bessel function and Newman functions, they will convert to this. J naught will be equal to sin k r and eta naught it will be equal to minus cos k r. Therefore, this equation becomes minus VR upon k, h cross square upon 2 mu is just to balance the dimensionality. And this equation is numerically integrated from original to asymptotic region using the fifth order Runge-Kutta method. Now, the K wave number is related to the, we already know this thing, the center of mass energy by relation this, and where ECM is related to lab energy by this relation, MT upon MP plus MT, where MP and MT are the masses of projectile and the target respectively. Now, to obtain the phase shifts, we have solved our phase function equation by using the Runge-Kutta fifth order method, and in this method we only require the interaction potential. So we also calculated the mean absolute percentage error with respect to the experimental data. It is given here, the references. So the mean absolute percentage error is given by 1 by n and delta I E minus delta naught upon delta I E into 100. This is the formula. So these are the model parameters of the relative jump potential to obtain the scattering phase shifts for 2s half state of real and imaginary part of the phase shifts. So for the real part, we can see that the depth of this repulsive part is very high as compared to the imaginary part, and this is for ND system. And for PD system again, we have got 913 as a depth for this, and depth for the imaginary parts are reduced little bit. So it means that there is a very less contribution of the imaginary potential to the phase shifts as compared to the real parts of the phase shifts. So this the empty potential plot and the phase shifts for ND and PT skating, these are shown in these figures. So in this figure, this is for ND. This is for ND part. So this is the real part of the phase shifts, for the potential for the real part of the phase shifts, and this is imaginary potential. You can say that this is the complex potential, and these are the real phase shifts. These are the imaginary phase shifts. The imaginary phase shifts are the positive parts of the phase shifts, and correspondingly their potential is very big till 3 fermi-meter, where there is a neutron breakup threshold. After that it smoothens. The potential smoothens means the phase shift also smoothens with respect to distance r. Here I am not plotted this phase shift with respect to r, but if we plot this phase shift at particular energy with respect to distance r, it will get smoothened at above distance 3 fermi-meter. So next, this is for PD system. This is for real part of the potential, and this is for complex potential. And these are the real phase shifts. These are the imaginary phase shifts above zero level. And so this is the conclusion of our research. We have obtained the real and imaginary part of scheduled phase shifts, and by using phase function method, the method joint potential has been taken as a theoretical model of interaction, and the phase shifts we obtain are having the mean absolute percentile less than 3%. So thank you so much.
Thank you so much. Our club is now open for questions. Please ask some questions so that so now you have done the ND, PV, etc. You started the NN potentials to begin with. Now, are there any plans to take it further? That means you want to go for complexes like helium-3 versus neutron, protons, scatters, and things like that?
Yes, we did actually. Our group with Anil
Stop.
has already done this.
Oh, thank you so much.
Sorry.
No, better. Thank you. Yeah. So that's already done that. I see.
It's done for neutron proton.
Actually,
Further asking, are you planning to extend this work to further?
Yes, we have extended this work to NL.
Because we just have alpha yesterday, I don't know that, yeah.
Yes,
We talked about that, yeah. So ultimate goal is to reproduce the exponential phase shifts with metal charge on potentials and the phase-space method, right?
Yes, sir.
And then take it down to the undergraduate level, sir.
Yes, sir.
In Indian University. That will be wonderful insight. Any questions? Because you're all MSc students, so if this is going to undergraduate level, then you must be able to understand or ask questions about it.
The question is complex potential. Its significance. I understand, but what is the complex potential? Show that there
What is significance of a complex potential? That's what he's asking.
Actually, at a certain point, when there is a breakup threshold of some interacting nuclei, after this, before that we have elastic scattering process. But after the breakup threshold, we also obtain this inelastic processes along with the elastic processes. Okay, so these inelastic processes result to the absorption cross section, which we calculate, which we obtain experimentally. So from these absorption cross section, in that if we define it analytically, the formula for absorption cross section contains a term 1 minus eta L. This eta L is the absorption coefficient, which contains the it is equal to minus exponential minus imaginary part of the imaginary phase shifts. So these imaginary phase shifts we obtain by assuming that the potential we are considering is also a complex potential. So by calculating our potential like this, then V will be equal to V real plus V iota V imaginary part of it. So Dirichlet was first person in 1965. He gave this formula to calculate the scattering phase shift for imaginary part by using the complex potential. He did it for alpha scattering, and we then calculated it for NDPDL system by using the phase function.
In one sense,
Inelastic scattering. That's the absorption.
in one sense, what it is, in an imaginary component, when you put a potential, it removes the flux from the incoming release current. It's an absorbing part. So that absorbing part can go anywhere it wants to, but that can be modeled in terms of a complex potential. That's what they do. So I thought that it's not it's a challenge, but it is just to ask that I'll give him a simple, wonderful, very well done. Thank you.
But the sir's question remains, scattering phase shifts, are will be reduced from the experimental cross section. So where the experimental cross section?
The second part I am not knowing.
First question remains unanswered. That's it. That's a very good
That's
job.
something future work you have to do.
No, that's it. That's it. Very good job. Thank you so much.
Only when you calculate the cross sections, then you can be sure that you are able to match with the experimental.
Okay. Good. Then what
There's
else?
only one more step ahead, but that completes the process. Otherwise, it doesn't complete the process.
Very good. Thank you so much. Now, Lalit Kumar. Lalit Kumar.
Next, Lalit there?
Yeah, next is Lalit. You control your time.
Myself, Lalit Kumar, I am presenting my topic on construction of generalized inverse potentials using machine learning. So these are contents of my slide. First, I talk about what is the methodology I am using, and then talk about what algorithms I am using, like global optimization algorithm. Then I check how this global optimization algorithm works when I remove one point from a data set, and from 2 points from the complete data set, and from a 3 point group. And then we see how the combinatorial data analysis happens. So first we are modeling N alpha, that is sequence parametric plane, using Morse potential. This is the interaction potential which we are using in the phase function method for obtaining the scattering phase shifts. And this is the phase function method, and this second order differential equation is converted into non-linear differential equation, which is called the phase function equation, the equation 3, and which is VR is the interaction potential, and these all things is cos delta and GL and beta delta, the Cartesian and the Cartesian functions. And equation 4 and 5 are the generalized equations from where you can obtain these Cartesian and the Cartesian functions for the different L channels. And for L equal to 1, that is for the P partial wave, this delta 1 point is equal to cos of k1 delta sin kr upon kr1 is cos kr plus sin delta kr into cos kr plus sin kr. And now what is the advantage of this phase function method? It requires not use of wave function, it requires only the interaction potential. From there you can obtain the scattering phase shifts. And by using the optimization technique, we optimize the first parameter, potential parameter, and obtain the scattering phase shifts. So what are the metrics that we are using in this term? We are using the mean absolute percentage error for minimizing our data with experimental data. So, but here now I will talk about the global optimization algorithm. The global optimization algorithm or the algorithm which uses the complete data set to minimize the function, that objective function, to minimize it for the complete data set. For a local optimization system, that it can be served as it can solve only for a 2 or 3 points for which the error is minimum, not for the complete data set. In case of local optimization algorithm, it minimizes that function There the overall error is minimized with respect to the complete data set, not for a input search for some regions for the input data set. So, firstly we have 22 data points which are from the Sechler analysis. They are called experimental data in literature. So we write the experimental data and obtain and remove one point from a first we complete data analysis of the global optimization algorithm, and then we obtain these parameters from for P3 half state, the resonance state for an alpha system, and obtain the V0, RM, AM alpha 58.308, 1.632 and 0.505, and with overall make of 1.37%. And they are the scattering phase shifts. In fact, so the resonance region, there it is matched very well, and there this is the interaction potential which is responsible for the scattering phase shifts. And next we have to check the data sensitivity, that what happens when we remove one experimental data points from a different regions. So firstly we got 21 combinations from where first point is removed, and then second point, third point, fourth point, and when first point is removed, the overall optimization taken with respect to the left point. So there are 21 points are taken for the minimization, and we obtain the set of parameters which is given in the second row with the 58.394 plus minus 0.85 for the V0 and RM and AM. First row with the global optimization algorithm, where there is no point removed, that is we have obtained this for the complete data set. And we have the potentials, they are the scattering phase shifts corresponding to these potentials from where this black line for the global optimization, and this maximum minimum correspond to the standard deviation to the plus minus to the scattering phase shifts, and we have the results. And next is the what are the potentials, and the difference in this potential is very small. So the one region from the inside is shown here, which you can see that there are the three potentials which are close to each other, and in the single frame this is not visible to you, and they correspond to the same phase shifts. And next, but the second point is the 2-point removal. So for 2-point removal, we do the 22 C2 combinations. Two particular combinations are analyzed at a time, and then we saw that only 25 combinations have the wave of less than 1%. And then we average these all waves and the parameters, and we obtain the third row, that is 58.246 plus minus 1.13. And now, similarly the RM and PM values got, and with the overall wave comes out to 0.16, which is greater than in the previous case, which is 0.138. In the global optimization case, this is 0.137. And we have the scattering phase shifts, corresponding scattering phase shifts, and next is the potentials. And now what comes out when we remove the 3 data points, and there are the 19 data points in the sets, then there are 22 C3 combinations, that is 1540 combinations are analyzed for each case, and out of which 1450 combinations is found to be the make of less than 1%, and all the combinations data is averaged over this range, and we obtain the fourth row, which is 58.94, and the overall make for this case increased to 0.183. This is the 3-point removal. Now what happens, we are the scattering phase shifts for this one, and the potentials, and what is the combinatorial data analysis, in which case we have firstly removed the 3-point analysis and done the COA for the complete set. Now we have the 3 parameter potential, Morse potential, V0, RM, and we have taken the 3 experimental scattering phase shifts to obtain the scattering potential. So for 3 3-point combinations we minimize our wave, and we obtain the 1540 combinations, and out of which only the 65 combinations are less than 5%. And from these combinations we fix the one parameter, that is Rn. And from that Rn now we have only the two parameters, that is V0 and Rm, to minimize. So that we have only the again 231 possible combinations, from that we are fixing the Rm value. And then again we run the optimization algorithm and obtain that from this we have the potential parameter, then we run by fixing the Rm at 1.610, we obtain the V0 and Rm in 56.253 and 0.52 EM values, and the overall waves come to 0.398%. And the scattering phase shifts for this CDA, and this is for the digital inverse potential, which are responsible for the scattering phase shifts. And here the table is the computing table, but the first row is the global optimization algorithm, where the 22 experiment data are taken at a time for the global optimization. And second point is the data sensitivity analysis, in which the one point is removed at a time, and 22 combination analyzed and the overall average is given as 58.39, and the overall MIP increased to 0.138%, previously it was 1.137%. Again, the next 2 points removal, then we have 2 combinations, 31 total combination, from which the combination which are the for which the overall MIP is less than 1% are taken, and the overall MIPs come out to 0.160%. And the third one is the third data sensitivity one, where the 3 points are removed at a time. So we have 22 C3 combinations, that is 1540 combinations, out of which 1540 combinations gives the MIP of less than 1% and with the overall MIP of 0.183%. And the third one is the combinatorial data analysis, in which we have the 3 parameters and the 3 scattering phase shifts. And we obtain firstly we fix the one parameter Rn by analyzing that for the overall 5% of the combinations, 5% combinations that gives the overall MIP of 0.13, and for which we fix the 1.61 Rn values, and then we redone the optimization for 231 combinations, for which 265 combinations with the MIP of less than 5%, and this is our final results. Thank you.
Questions?
So in a phase function equation, we use this Basel and Newman functions. So is it because of that you are using some plane wave criteria, or there is something else? What is the logic behind using these functions in this phase equation?
So because of the scattering due to potential, the phase of the...
My question is, you can use any function, right? We are using Basel function. So what is the mandate there?
डेरिवेशन डेरिवेशन में क्या कर रहे हैं? डेरिवेशन यहाँ थोड़ी होगी. Sir is asking why are we getting spherical Bessel functions?
The solution of the equation beyond the potential is a sinusoidal, and these functions are the free wave particles. They behave like the sinusoidal functions, so we are using these functions.
Basically, in major equation when you take, there is an element plus 1 by us, the centrifugal part. So with the centrifugal part, if you make potential 0, right, the solution gives you better solution.
So with that assumption in mind.
So basically, it actually comes out. What is the idea of phase function method is, you're starting with time element Schrodinger equation, and then trying to reduce it to a Riccati equation, first order. And the process, what we are doing is, we are actually trying to use the concept of logarithmic derivative being continuous across the boundary. So that is a very interesting thing actually. What do you mean by logarithmic derivative being continuous? But what here? So let us move to CR2. Okay, that is some special guests who are coming from Goa. So I told them that when they come, we have another two okay, come, let's go. So just on the next class. Okay, but we are going to work on it, right? We should give 1 off, 2 off, 3 off. Where we stop. After the lunch, we'll come back here. After lunch, we'll be back here. Just now we'll go to CR. There's a sequence here.
Checking from the sensitivity when 1.0.
Sir, we'll continue questions there. We are not going to leave him. And then we're going to continue the next talks, right? No, even questions.
Sir, talks will do there. That's what they're saying.
Sir, just please come with us.
I understand that, sir. Thank you.
लैपटॉप किसका है? ये भी लेना।
सर ये खोलना पड़ेगा।
इसको यहीं कर दो। निकाल दो। ये आपका? नहीं, इसको रहने दे पूरा ये। और लैपटॉप? लैपटॉप को रहने दे ये। अकाउंट नहीं कर रहा है।
लैपटॉप भी लेकर आना सर।
हाँ, लैपटॉप को ले जाना पड़ेगा। चलो चलो वही करेंगे। वाइट को ले सकते हैं। यहाँ कोई और है? अच्छा, यहाँ किसी और के टॉक है। ओके। नहीं, चार्ज वगैरह भी ले जाओगे ना अपने अपने, जब यहाँ कोई और आ रहा है तो। चार्जर यहाँ किसकी टॉप है? इसके कौन लाए साहब? किसका? इसको ले जाना वाला पर किसका होगा? लड़की का होगा। चलो चलो फिर। उठाओ उठाओ। चलो चलो। टू खत्म हो गई तो बोलना तो कहाँ है? क्या हो गया? अब तो होना ही है।
Today is the last day. Tomorrow it will be online. Morning to evening. On the system. Sunday afternoon. Today actually Zoom also supposed to go on. Tomorrow all presentations are I got more. That is for the 9. Ready for that. After you do something on the place, this is for you. That's for actually if you eat banana or something, actually you were getting very perfect results. So then some reviewer asked how sensitive is your result to the data. Then we thought, actually getting too much of an overfit also is not good. Generalization is lost. So that's why this paper is fully only on understanding how to do the analysis. So analysis also is very important. Actually without analyzing much we should pick the machine learning. So machine learning में ये problem होती है overfit हो जाए. So how to ensure that overfit is avoided? Because we are trying to force it, right? Just trying to force the equation. It's a good tool to do it, but here you have to probably take care of the modality. So then only the data is over. If the data changes tomorrow, then our production will change. So should we not use some range? That's what we call it. So that's why this different types of analysis. So one is, especially some people are getting doubt. Theoretical physics is always been model से prediction आना चाहिए. अब क्या करना है, जितना भी डेटा है उसका पूरे डेटा पे 10 मॉडल लिखा है. That's why change one production. So then we thought, okay, what is the way to do it forward method. So that means number of equations you want to solve should be equal to number of model parameters. Right? Otherwise it's over. So that means you should not use all exponential parameters. You should use only definitely exponential parameters. As many as your parameters. There is only combination which one to take. Typically, generally, you will get the everyday and that's something that you get. But that doesn't happen because here the potentials are energy-equal. Physics में हमारा potential जो है energy-equal potential. तो energy-equal potential after you take one energy, energy data will not get potential model. Because the energy when you spend a lot of time and able to be adapted. Yeah, could you connect? Yeah, shifting means there is always some time in a teacher or a child. The main problem that we have faced is people simply give the model parameters. They do not explain how they got it. In all the papers you see, they will see that these are the parameters, optimal parameters, and this is the result. Nobody gives the process of how we can obtain the model parameters. We don't teach in the class.
That will give the insight of the...
Exactly. The shell model will be, or the graph model will be. We never bother to derive the explain the parameters. We simply make a parameter there, look at put it and then say that it works.
That's the reason you have so many different sets of parameters.
Then we realize what is exactly happening. That's why we are asking the question. That's why we put our model. But Royal's data, we are taking the same data, but we are not getting the same result. Then we started wondering where the problem is. That formula which we are using is given in all these data. Last time we asked this question, we are not getting the results. Then we went to some other place, there we got the result. Then of course, this time in DAE, we mixed the two models. Samantha's model and Royal's model. Samantha model is very good for A less than 40. So if you understand the process of optimizing model parameters, then you can play with new models. Otherwise, we don't know how the results are. Absolutely. I think we are got set now. Okay. Yeah.
Thank you very much.
Yeah, any questions please? I think we could not take all the questions there because we have to make a shift.
Mr. Raj Kumar.
So I have a question. When we do practical work and when we match our practical with the experimental worker, then there is some error. So this error is due to which parameter that the error between experimental and practical work. And if we can because in particle scalar, a small error is very important due to perturbation.
So did you understand the question?
If I am doing experimental work, how do you also
We have not done the experiment, we are using
I am doing experimental and you are doing practical work. Both are same, result are matching, but there is small error
So we have to modify the
difference. So this difference due to which parameter can we minimize this gap? Because at a particle scale, a small gap, a small difference is very important due to perturbation. So can we minimize this?
We have the complete knowledge of the interaction, then we can overlap those two results. If there is some discrepancy, maybe in the theory or maybe in the experiment, so then there is a difference in these two results.
It is due to both.
Maybe the experiment is not with the accuracy, or with theory there is not a proper understanding of interaction, but what parameters we have to take about the interaction they are responsible for, so that there must be a accuracy. Otherwise they overlap. We have to
See, that is what is theoretical modeling all about, right? Yeah, what you are doing. If something is fitting, say for example you have taken square well, it didn't give answer, you took harmonic oscillator, it gives somewhat good answers. Right, but something it couldn't explain, so you drop it, then you went to Wood's action potential, like that. So it's not that the same parameters can be changed.
Yes.
You change the model of interaction. As you said, maybe perturbation. So you added L dot S term. That is a perturbation like thing. Okay. And then you calculate. So it's always a process of completely refining the theoretical model to give a better
explanation for the experimental data. But as he said, if experimental data has noise, then what happens? So that's why we give plus minus. Not only in theory, experiment, but also in theory also we give plus minus. So if there is a good amount of overlap between the theoretical margin and the experimental margin, then you can say, okay, theoretical model has been successful in explaining the experimental. That's all.
Further questions? Okay, thank you, Ravi. Thank you, Ravi. Now, our next speaker is Aditi Sharma. Please come along at the table. She's going to tell us. N-oxygen system, phase functions.
So for studies by output numbers, it can be shown that the most potential is 2 with less potential to study the scattering phase shifts for various nuclear or other nuclear system. So getting motivated by this, I took such a nuclear system, that is the N-oxygen system, and therefore the criteria is to study the N-oxygen, 16 oxygen using the phase function. So here's a brief outline of my talk. I will go to motivation, then the methodology discussed, then ambitious research, and followed by the conclusions. Here is a brief motivation. Because the reaction of the derivative and oxygen capture, that is a part of the chain of thermonuclear reactions that led to the formation of the sun stars and therefore the entire universe. So it is worthwhile to be considered. To calculate this reaction, it is necessary to know the potentials in its resonant states, that is 2p3 and 2d3 but here I will consider only, I go for 2d3 state, and I organize my work according to the simulation methodology which we have given, whose construct is to construct the theoretical model for the problem at hand by describing the various interaction laws and the dynamical laws that governs the motion of the particles. After constructing theoretical model that needs to be solved either by using analytical technique or by using numerical technique. So here we are utilizing numerical techniques and obtain its numerical solutions. These numerical solutions are further used to determine the phase shifts for the 2d3 resonance states, and these phase shifts are further utilized to calculate the partial cross-sections and the resonance energy for the same. So I'm going to define the interaction model for interaction for the model. So interaction potential that we considered here is most potential, which is the two-term potential, and given by V m of r. So since the binding energy of 16 oxygen is 7.97 MeV, therefore it is necessary to consider the potential that is attractive in nature. The method we are utilizing is phase function method, which is a linear homogeneous equation of second order that is used with first order non-linear differential equation. This interaction potential, that is the most potential, is to be substituted into the phase equation of this phase function method to for getting the phase shifts. The phase equation is given by this delta LP of R, which is a combination of the Bessel functions and the Newman functions. Here, this equation will give the phase shifts at a particular energy K for the nth partial wave. Here, the K is related to the energy in the center of mass by this ratio square root center of mass, E of center of mass divided by h cross square by 2p. For L equal to 2, this phase equation reduces to this type. So this is the whole methodology which is organized in the form of the flow chart. Firstly, the parameters need to be initialized, that is for the most potential, and these potentials to substitute into the phase equation. This phase equation is to solve using the Rudek RK5 method, and
after solving the phase equation, we got the simulated phase shifts. Then
स्क्रीन की तरफ भी करके टास्क देते हैं ना पॉइंट अदरवाइज ऐसा लग रहा है कि हम स्क्रीन कर रहे हैं किसी को
these simulated phase shifts, using the simulated phase shifts and the experimental data available, calculate the map. If the map is less than the tolerance, then these are the optimized inverse potential parameters. If the map is less than the if the map is greater than the tolerance, then again the process is to be followed. So this is the potential plot using the optimized Morse potential optimized parameters with V naught 77.619 MeV, Rm is the 1.039 Fermi, and Am, which is the shape parameter, comes out to be the 0.993 Fermi. In the extreme right hand side, we obtain these simulated phase shifts that are plotted with the experimental ones. So this phase shift, now using these phase shifts, we move further to calculate the partial cross section. The partial cross section for the Lth partial wave is given by this, and for the D wave is it reduces to the 25 by k square into sin square delta d. So I plotted the partial cross sections with the energies in the lab frame, and we got the resonance energy at the 1007 MeV, whereas the experimental resonance energy is available 1000 plus minus 2 MeV. So it can be shown that this it can be shown that our simulated value, simulated resonance energy is on par with the experimental literature reported value. These are the conclusions. The molecular Morse potentials have been considered as a theoretical model of interaction for determining the phase shifts of 2D 3/2 resonance states, and these phase shifts are utilized to calculate the cross sections and obtain the resonance energies. In the future, we would like to study other astrophysical reactions such as the N12 carbon, P carbon, 4 medium 12 carbon, P13 carbon, and so on. And also, these results needs to be further enhanced. So, thank you so much.
So you talked about thermonuclear reaction, right? So is it same as that of thermonuclear reaction, or are they different?
So in thermonuclear reaction, there is.
नहीं पहले तो सेम है या डिफरेंट करती है किसी भी न्यूक्लियर रिएक्शन को मैं थर्मोन्यूक्लियर रिएक्शन बोल सकता हूँ कि नहीं बोल सकता नहीं बोल सकता क्यों
Normal reaction और thermonuclear reactions में same नहीं होती है.
मैं बताऊँ ना क्यों
Thermonuclear reactions में these are the radiative reactions. The energy is reduced, and this just like we in normal just like we talk about the fusion and the fission reactions, lot of energy is with the product formation. This product is further split into the number of
but
the
energy is released in both the reactions, isn't it?
Yeah.
So what is the point of difference then? Anyway,
आप कौन से रिएक्शन के बारे में बात कर रहे हो? एस्ट्रोफिजिकल रिएक्शन ना? व्हाट इज एस्ट्रोफिजिकल रिएक्शन मतलब क्या कहाँ हो रही हो? सन की टेम्परेचर
okay, so one more thing, you are talking about your radii, RM or whatever you call it, up with accuracy of 0.039 for me. So, do you think it is relevant now to talk about radius of the range of some 3 or 4 decimal places? You do theories, you can go up to any number, okay? But is it relevant in reference to the present understanding what we have?
आपका पैरामीटर्स का जो डेसिमल प्लेस आप दिया है वो सही है?
They're very saying very important.
Yeah.
That's what they ask.
So आपके हिसाब से जो हमारी आज की experimental या movie understanding है, so according to you, what should be the appropriate way of writing it? Have you idea or not?
आपका एक्सपोनेंट डेल्टा की एक्यूरेसी क्या है? हमने डेसिमल प्लेस कर
3 decimal places.
Well, I do it. I can make it even up to 10 decimal places. That's not a problem.
नहीं, now एक्सपोनेंट डेल्टा is up to 3 decimal places, but theoretically आपके कितने decimal places दे सकते हो?
There's a question for you. Let's get it. The neutron radiation is about coordinate frequency. The proton is about coordinate frequency. If you say a distance is like 0.045 or whatever it is now, it's a 1/10 or 1/20th of the size of the radius of the neutron, right? Then it will be making significant impact upon how we understand the phenomenon.
Yeah.
That's what we're asking. See, that is very physical significance. So, in fact, this is the kind of a problem we always face, not only the students.
So as a student, you should actually know that.
No, the faculty also made up, but they produce all the decimal points are given by the programs and so forth. But then, but that see, when you are looking at the tricks like this, you use parts. So, you can more of picture when you're going to go after decimal points, really attention to that. Then you miss the main point, in fact. That's not the point.
Yeah.
ऑनलाइन
Possibly telephone the other side of this.
कल पे कर देते हैं हाँ अब आ जाएंगे आ जाएंगे विश्व को बोल रहे हैं आगे सर आगे आफ्टरनून में हम सेशन और
इसी के बाद है सर एक सेशन और इसी के बाद एक सेशन और है सर
नहीं दोपहर को तो मनोज शर्मा सर किया था
उसके बाद प्रेजेंटेशन का सेशन
लंच के लिए जाना है क्योंकि लंच नहीं तो वहाँ फॉरवर्ड करेगा उस लड़की को बोल देना post in the second session of whole presentation she can start okay हमारा नहीं नीचे आ
Because of tolerance, we have limit change करते हैं तो the data जो आपको calculated data given
और मेरा लैपटॉप
means it depends upon the value of the tolerance you are setting. If you are setting to a very small value, then the difference between your capital and actual value is small. So entirely depends upon the tolerance.
See, basically what do we do, sir? When you do the entire analysis, that's why that analysis talk was very important. Because we always tend to have 6 decimal places. But when you're running about all this, you get 8 decimal places.
That's what I say. You can go to buy.
So we move to the experiment axis. So the experiment the data is accurate to 3 decimals or 2 decimals. Then we keep on reducing the norm. You will keep running the code 8 decimals to 10 decimals.
But you
round it off.
You bracket it.
You round it off such a level where it actually matches with the experimental. And this is actually allowed in our lab scenarios. Whenever we will have experiments.
It's a long practice.
Normally what we do is we always keep 1 decimal place more than what is required. And in the end you round it to the required decimal. So that's all it is.
What is this AM?
AM is the shape parameter. Shape parameter.
It has something to do with the definition? Or surface diffusion?
Yeah,
surface diffusion?
This term is also included in good section potential.
Surface. Okay.
RM is somewhat like the equilibrium distance.
You know what range of surface diffusion is you can take for any nuclear calculation?
Is it 0.9 and
No, that's why I'm saying we should not go like that actually. See, we are not talking about nuclear structure here, we are talking about nuclear scattering.
Is it 0.9 or 0.99?
0.99 sir. Here AM is not that surface diffuseness that we are talking about. So there the surface diffuseness generally goes between only 0.6 and 0.7.
That's what I was wondering.
This actually talks about the tail. See, more like you should look at it as Yukawa tail. How the range falls off for the pion exchange or the meson exchange.
So basically you are not taking any surface diffusion, you are taking what?
No, in fact there are no physical.
Taking 0.993 or 1 is same thing.
No, it will change. From different systems it will change. What we have to understand is, this is not actually a forward process, where we try to physically determine a parameter and put it there. Okay, see this is when you take a Hooke's action or something, you are seeing some physical parameter like density. So based on that you are modeling. Here this is called reference potential approach. This is actually inverse approach. So here, like basically you are fitting a mathematical function. In fact, we don't even need a mathematical function. I can simply initialize all the values of potential to 0 or some randomly and then start the process. So by itself it will bubble. It's a one-way approach. It will bubble by itself and come to the potential which is explaining the experimental static.
So this is the number which you get from your calculation.
Yeah, but no, here we are guiding that number.
No, my only worry is this AM is a given parameter or generated value?
Generated.
Okay. There is not a difference.
It's not, yes. It's not physical.
Yeah, it's not physical.
So it is a mathematical function which allows you to obtain the interaction potential that is responsible for the static equation. That's why I said this is basically like not forward modeling. Yeah, it's reverse modeling. It's like more than machine learning. So you have all the data. What is the best model that represents the data? Yeah, that's it. So that's why it's actually we are struggling to make people understand because this is not the regular way in which they think this is thing. So सर अभी लंच करके आएंगे निशु को हम बोल रहे हैं कि आफ्टर सेकंड सेशन में हमारा और प्रेजेंटेशन तब वो शुरू करेंगे क्योंकि वहाँ ऑलरेडी लंच लग गई है और हमारा टीचर्स वेट कर रहे हैं all the CRS here we are going to the canteens टीचर्स के लिए कैंटीन में रखते हैं बच्चे खा सकते हैं हम यही आएंगे ना I don't know how long it will take वो हमारे बोल रहे थे आके देख लेते हैं अगर वो फ्री हो जाए तो वही करते
अभी तो चलना है अभी यहाँ कोई छोड़ना था चलो हम इसको भी रहने देते हैं मैंने लिखा क्या था प्रेजेंटेशन में वहाँ भी लगा होगा ना सब में अभी चला है ना
I think after session में आप लगा ही लोगे ऐसे
खाना खाने के बाद ना लगा ही लोगे सर तो बोल देंगे
सेमिनार रूम के बाहर लगा क्योंकि बाद जब आएंगे ना तो आप हम दिखा देंगे अदरवाइज जो बैठ तो फिर बाहर क्यों निकलेंगे है ना
प्रोसेस से बात हाँ इसको भी बंद करके रखो ना ऐसे ही ऑफ करके रखो स्टॉप प्रेजेंटिंग होगा ना यहाँ ऑप्शन हो गया है स्टॉप हो गया अच्छा नहीं हुआ अभी स्टॉप हो जाएगा अभी वो यहाँ लग रहा है इसको रहने दो ऐसे ना
Wow,
Thank you.
एक तो मैडम थी ना वो उसने
बॉल पार्टी ऑफिसर्स के साथ BMW गई अरे ऑफिसर्स की बॉल पार्टी नहीं होती जो ऑफिसर एनडीए वाले होते हैं एनडीए ऑफिसर होते हैं ना उनकी बॉल पार्टी जिसमें उनकी गर्लफ्रेंड या वाइफ ऑफिसर होते हैं सीडीएस एनडीए से एनडीए वाले नेशनल डिफेंस सर्विसेज कोई भी से एनडीए वाला मुझे लगता है खाने को हाँ तभी लगा है